Okay, so here we are. Welcome to the June meeting of the FORTH2020 group. And we have an exciting program here as well. That's not, I'm saying that because I will be the first speaker, but all the other talks will be very interesting. So yeah, Peter, are there any important things you want to say up front? Shall we just start?
Not really, Ulrich. I say hello to everybody. Nice to see you all. And we are going to see today a very interesting demonstration after Ulrich's talk. Then I have in the last part of our meeting, we have the coffee break. After that, we have Don and we have Brad, and we have also the a little chat. So everybody who has something with ESP32 force or has questions or etc., please join the last part of the meeting, and you are free to talk. So reserve questions, etc., for this moment when we have more time. Okay. Mm-hmm. I present now Ulrich Hofmann. Ulrich, are you ready for your talk?
Yeah, I try to share my screen and then we will see what happens. So here we go. Aha, Facebook. No, that's great. So you should all see the slides. There have been some discussion on how we can bring up beginners of FORTH up to speed. And so I was thinking about giving maybe a sequence of tutorials facing on different aspects where I think it's good to know what the typical approach actually is. And I thought data structures is probably something that we can start first, and then we can see how we continue with these things. So it's not a introduction like FORTH has a stack and you use it in a certain way, and these are the stack operators, and it's a reverse Polish language. That's all a beginner really very easily grasps. But it's more in the things, how would you do certain things that you are assuming in a programming language in the first place. And you find that you have to have knowledge if you want to do that with FORTH. And so I will talk a little bit about FORTH and features, maybe the missing features that we add. And then FORTH and memory, and then we will have a look at how to define what other programming languages call structs or records. And explicitly, I will not go into how to define objects here because we want to look at beginners. And so we first grasp the easy parts or the more easy parts, and then we can continue with objects in a later talk. Yeah, and then we finally come to some conclusion. Maybe we have some discussion after that. So the idea is not to have the best and clever thing, but to explain something like best practice or common practice that we want to do. If you follow discussion with people that are new to FORTH, then you often hear something like, well, FORTH does not have feature X, no dynamic memory allocation, or it doesn't have graphic support or whatever, and no support for data structure. So you can't just go ahead and define a data structure easily. And the seasoned FORTH programmer typically answers, well, this really depends on the application, and you define the feature that you want to have so that it fits the needs of the application. And you can do this very easily in FORTH, and you just go and do it in an appropriate way. So might be a case statement, for example, or it might be structs, as we talked today, or objects, or arrays, or what have you, a string manipulation, and things like this. And so, yeah, in FORTH you do that, and you take the memory layout for your data structures, and you plan the memory for structs, for example, and you do this on your own. There is no library where you take this from, but how would you do this? So if we had some discussion on how libraries can come into place, or how we can benefit. So sharing of ideas seems to be a very good thing. And so this is also part of that, explaining how I would think is a best practice approach to do these kinds of things. So let's have a look. So FORTH and memory. And in FORTH, the memory is exposed explicitly. So it's not as in other programming languages where you always have named variables that deal with this, but you can just see the memory and the layout. You can inspect it. Many systems come with something like a dump utility where you can inspect the memory and how data is stored there. And so as an example, let's think of some data memory area with some arbitrary addresses here, and the content, so in one byte, the number 8 is stored, and then the representation for the appropriate letters, for example. And you access the memory. FORTH has a stack, as we all know. You access the memory by using cfetch and cstore, or fetch and store if you don't want to access single bytes, but want to access words, whatever that is, or cells. Then you would use fetch and store, and you put the appropriate items on the stack. And one common representation of strings, for example, is to have the length of the string as one character in the first character of the representation, and then the string itself in the remaining bytes that come up. So-called counted strings. And if you want to deal with them, you can either put the address on the stack, 2100 or V, or you could use the count operator on this. This will put the address and the length on the stack to deal with this. And we have stack pictures that describe things that are on the stack, something like this. So if you want to access the individual characters, you have to do address calculation. So you have to go from the base address of the string to some of the other addresses to fetch the appropriate bytes. So if you want to, for example, fetch the T of FORTH 2020, then you have to add the 4 to the base address and get there. Yeah? And you have to think about how to do the appropriate calculation and do these things. Right. So if I'm now naming the memory, I can do this with create. I can name memory areas, or addresses are just normal data in FORTH. I can store them in variables or what have you, in values. Then you can say something like V, which gives us the address of 2100, count, which gives us start character address and the length, and type, the operator that takes address and a length and displays this on the terminal. So this displays FORTH 2020. So, and the programmer knows about all this. It's exposed, it's not hidden, and you have to know about that. So if you just want to display FORTH, you could just say 2101, the address here, and put that on the stack, and 5, which is the number of letters in FORTH, type, and then it would just type out the prefix and not the whole string. So it's up to you to do it as you want. Right. So summarize. FORTH exposes memory explicitly, and you access it via fetch and store if you want to access cells, or you use cfetch and cstore if you want to do this on a byte basis or character basis. You reserve memory in the FORTH dictionary, which is a bump allocated memory that is available to programs. With create, which names a cell or an address in the dictionary, and you reserve space with a lot, where you give the number of bytes that you want to allocate, or comma if you just want to allocate the next cell and store the value in the dictionary, or C comma if you want to do this with characters. Right. So, for example, if you want to have variables where you can store a single cell value, then you can define variable as create 0, comma. So it allocates one cell, initialize it with 0, and gives it an appropriate name so that you can name that memory area or address that memory area with the name that you have given. Right. And so if you want to access different parts of your data structure, you have to do address calculation. So the plus operator is your friend. It can also calculate not only with natural or unsigned numbers. It can also calculate with addresses. And so you can add an address and an offset to get a new address, for example. And if you're talking about cells and on different FORTH systems, the cell width can be different. So we have systems that are traditionally 16-bit, have 16-bit cells, and there are also today systems with 64-bit cells. And so if you want to do some portable things, then you have to abstract away the cell width and deal with that maybe with the word cells. That takes a number of cells and gives you the number of address units that you would take to actually do the appropriate address calculation. And we already saw count, access the length field from a counted string. Or if you want to iterate over a memory area within a do loop, and you only know the start address and the length, but the do loop takes the end address and the start, you can take the operator bounds, which astonishingly is not standardized, but it's commonly defined as over plus swap. Right. And so let's have a look at some memory area. Say we want to define a structure or a record. If you want to define what is a structure, then you can say it's a collection of fields. And a field can store some arbitrary value. It could be a character, it could be a cell, it could be a record itself, or it could be a pointer. It could be an execution token or whatever you want to store there. It's exposed to you and you manage the memory and do it as you want. As an example, say we want to define a record with two fields, X and Y. Think about maybe that's coordinates in a 2D space, and you want to deal with points there. Yeah, and so you have to allocate sufficient space to store the X and the Y value. Here I'm assuming we have a 32-bit width cell, so we have 4 bytes that are used to store some value in the cells. You can allocate the memory and give it a name immediately by create and give it a name P as an example. And then you can initialize both fields with 0, for example, or you can just go ahead and do the appropriate allot. Yeah, and here cells does the calculation. On a 32-bit system, it multiplies by 4, and so 2 cells is actually 8, and so 8 bytes are allocated for our data structure. So that's great. We have some space to put our data, and now we need to access the data, and we want to store something in the fields, and we want to read from the fields. And so you could do this and say, okay, 3p store, which puts 3 in the field X, 4p 1 cells plus store, or maybe there's an abbreviation for 1 cells plus, it's called cell plus, stores a value in the Y coordinate, in the Y field. And now p has the value 3, 4. Yeah, if you consider this to be a pair. And if you want to know the distance of this point from the origin, then you do the appropriate calculation. You do x squared plus y squared, and then take the square root. And then you know how far away the point is from the origin. So you would do p fetch, get the value of x, calculate the square, get the value of y, calculate the square, and then there's a plus missing, of course, and then you do a square root. And then you know the distance. So we're mostly concerned with how we access the fields, and that's not very pleasant in the moment. So what can FORTH do? You can do colon definitions, and you can give it names. So you can say, okay, I call X the same address as P, and then I call the second field, which is one cell apart from P, I call that Y. So this is doing address calculation, invisible address calculation here. It adds the 0 offset, and I optimized this already. And this does the appropriate address calculation for the Y, adding the offset of 4 to the base address to get the address where the Y is stored. And now I can say something like x fetch dup times to get the square of x, the same with y fetch dup star to get the square there, and then do the plus that I missed and that I copied on the next slide as well. Did not copy on the next slide as well, so plus square root here to get the distance of the origin. Much more readable, and so colon definitions can be used to name things, and so that's great. So we can do appropriate calculations and hide the layout of our data structure by this. So that's a good thing. So the normal way to write FORTH programs can also be used to do data structures. So let's look at a real-world example that we find, for example, in the FPC 60-bit DOS FORTH system. And it has lots of support for many tools, among them the ability to execution profile code. So you say, okay, how long does the execution of this part of my code actually works? And here there's a function defined that takes a double number representation of some time and stores it in this variable t time. And here we see variable t time, variable t time. This already allocates, as we saw, 1 cell of memory, and then he just adds 0, to have another cell. So t time is actually a area of memory with 2 cells, which is 2 times 16-bit in FPC, because it's a 16-bit system. And so what does this B to T word do? It divides somehow this double number and stores it in the first byte of t time, in the second byte of t time, in the fourth byte of t time, and in the third byte of t time. This is one way to do things. You just know the offsets and you do the calculation and store in the memory where you think is appropriate and do it. Yeah, this has the issue that after a while you can't remember what offset what was at what field what was at what offset. So you better comment on the result, and describe how the structure of your field looks like, or of your record looks like. Yeah, if you know the offset, if you write this, then it's all fine. But at least I am typically forgetting about the layout. So if you look into thinking force, there's a structure annotation style for with comments, and they look like this. So you use curly braces, and then you describe with the first letter how many bytes are used for the appropriate field, and then you give the field a name, and then you have a bar to separate the fields. And so you describe the layout of this 32-bit to 4-byte variable with this diagram. And then you can comment, or when you store there, you can write a comment, where do you actually store the value? Yeah, so tenths, so what it actually does, so it takes a double number that describes the number of seconds since sometimes, or number of tenths seconds since some time, and it splits it into appropriate parts, so you can store hours, minutes, seconds, and tenths of seconds in there. So if you add these comments, then that's great. You can better remember what's going on. But FORTH can do better, of course. We can name things, and that's what we should do. We should give it a name similar to the X and Y example that we did. Because what are the issues? You have this data structure, and typically over time you want to add maybe something. Maybe just having minutes and hours is not good. Maybe you want to have days in some way, so you have to extend this. And then do you add the new field at the end, or where it's logically reasonable? Maybe you have to adjust all the offset, all the address calculation that you're doing here. And it's very hard to distinguish between a calculation that is done for offset calculation or for address calculation, or something that is just done because of the application needs and has some other content. So the offset might change, and you have a hard time to change this, and you talk with someone who has gone through all the pains of doing these kinds of things. So this was for a 16-bit system. Maybe we have a different system, and then if you want to address cells, then you have to have different offsets. So as we saw with the point example, you better use cells to do the appropriate address calculation, abstract away the cell width of your system. Then porting it from one system to another is much easier than getting all the magic numbers. Yeah, we talk about these numbers as magic numbers because they are just specific to the FORTH system and to the layout of T-time and so on. And so, yeah, we really want to avoid these magic numbers in our code and abstract them away, at least give them colon definitions to do that. Yeah, and because we can't maybe not remember the offsets, then we can name them. Yeah, right. So for this example, what we can do is we can define 2 tenths, 2 secs, 2 minutes, 2 hours. To describe the appropriate address calculation offsets, and then instead of doing these with magic numbers, we just go here and do the appropriate address calculation and store the values. So, which is much nicer than this than before, and especially if you have the data structure comment just above that, then it's completely understandable how these magic numbers here show up. Yeah. But what we see is, well, more or less, they look all the same. They're doing address 1 and calculating address 2 and doing this offset calculation. And can't we factorize this in a way? So in FORTH, you typically don't want to repeat yourself. You just want to state things once and that do things, just name things again. So we want to factorize this into a common word that does address calculation, and then use this in the definition of the field names. So let's see how this could be. So what we can do is create a defining word A defining word is a word that is able to define new words, not colon definitions typically, but new words that have some kind of memory layout themselves. And if you take the defining word to create new words, then they would have all the same behavior, but they would have different data to work on. And so we're defining this defining word C field colon, which takes which takes some offset value and creates another offset value on the stack, and it also takes a name of the newly defined word that we want to define. And this defining word puts the offset value in its so-called parameter field and increments the offset value. And all the defined words will do the same thing. They will fetch the value from the parameter field and do the appropriate address calculation. So they would take a base address and add their appropriate address calculation, and this should be address 2 without the space in between. Sorry for the typo. Yeah, so we can use the C field colon word to define these byte-oriented fields that we saw in the example. We put a 0 on the stack because that would be the offset of 1/10 seconds. If we then execute C field, it will create the new word to tenths and increment the appropriate counters, the offset, so that now at this position, I would say at this position, there's a 1 on the stack, which is the offset of sex. And sex does the same, of C field does the same, defines the word sex now with the appropriate offset and bumps the offset. So we have a 2 at this point, ready for minutes, and so on. And after we define hours, we have the offset beyond our data structure on the stack, and we just drop it. We don't care about that for the moment. So we have now the 4 words, and they have exactly the same behavior as we had, as we did them before with colon definitions, but no magic numbers anymore. So that's great. We avoided them. And we just name the fields in the order of their appearance in the data structure. So that's great. We can deal with that. So we can just use them as arbitrary. So tenths is a word defined by C field. It has a 0 in its parameter field, and it adds 0 to the base address. And hours is such a field. It adds, or it has 0, 1, 2, 3 in its parameter field. So it adds 3 to a given base address. So that's great. And of course, as you would say, probably, well, tenths is something, it now adds 0 to the base address. And we saw earlier that if we do colon definitions, we can avoid this. Of course, you can define C field in a more clever way so that it will not do this redundant addition of 0 if you want to. And that's a whole area of challenges, how to actually make fields in the most efficient way. But we want to look at how they work and not how to make them especially efficient here. So, right. With the point XY, we saw that we are not only having character fields, C is for character field, and but we have fields of arbitrary widths, characters, cells maybe, or maybe a floating point number, or what have you. And so what we in FORTH typically look for is, yeah, a good factor, but some factor that is also general enough to capture a more general case, not the totally specific case, but something that is more general. And actually, in the FORTH 2012 standard, there is a word that is called plus field. That's similar to the C field that we just saw, but it takes two numbers from the stack. Not only the offset, the current offset, but also the width of the new field. And then it does the appropriate calculation, not 1 plus, as we saw earlier, but now it adds the length of the field to the appropriate offset. Otherwise, it behaves just the same, and you see the same typo again, copy and paste, bit me again. And then you can define something similar. You can define them, and now you say, okay, it's a character field. So you say, please increment the offset by 1 after defining this word here. And since we only have character fields here, that's how it works here. We give this. But now we can also say we want to have something like a cell field. And if we have a fixed number of bytes that we want to allocate, we just name the magic number, how many we want. But if we just want to have a single cell, we would say 1 cells field plus field to define this. Which brings us back to the point that we had. And so this is a typical structure that you would find in my force code quite often. If I defined the structure of a field, I use the plus field word. I put a 0 on the stack to say, okay, I'm about to start at the beginning of my structure, and then I put the size, or you can say the type maybe, of the field on the stack, use plus field to define the appropriate field name. And I'm playing around with the prefix for field names. You saw the greater sign to do the address calculation. Other programming languages use dot to do the field selection. I'm experimenting with underscore as well because it's seldomly used, and it shows what the intention actually is. So this puts 0 on the stack. 1 cells field defines X, increments the counter, so it's 2. It's 1 cell, 4 in the 32-bit system by now. 1 cells plus field defines Y with offset 4 and bumps the offset. So at this point, we have 8 on the stack in the 32-bit system, and we define the constant point here. And that's also a common practice that you name the data structure as well, and you define it as a constant that returns the size of the data structure. And that's great. You can use it for allocation. So you can say create P point allocate or allot, point allot to reserve enough space for a point. And you can use it if you start nesting data structure definitions. You can use it also in field definitions. So you can say something like point plus field underscore P, for example, to have a point field in a larger data structure. So if you define it like this, then you can say 3P underscore X store to store the X coordinate, likewise with Y. And then you can do the appropriate calculation again with the missing invisible plus at this, and then you would get 5 for the as the result, as the distance from the origin. So yeah, plus field is your friend. You can just go ahead and use it for defining things. I didn't go into alignment issues. In some architectures, it's not possible to store, for example, floating point numbers or even cells at arbitrary addresses, but they have to be aligned. So divisible by 4, for example, to store a cell in a 32-bit system, or appropriately aligned for a floating point. And the FORTH standard has also defining words that deal with alignment. But you can do this as well. If you use the word align, then you could say something like aligned 1 cell field, and then you are good because aligned will do the appropriate alignment of the offset for you as well. Right, so we looked at address calculation and saw that FORTH exposes memory. And so if you want to deal with data structure, you have to do the address calculation on your own. For structures, it means that you do offsets from the base address of the structure to a particular field. And you can either use colon definitions if this is something that is not worth having a defining word, or defining the name of the field. You can just go ahead and use colon to do that, or you use plus field so that you can even hide the magic numbers and just describe the layout of the structure that you have. So that's my today's talk on data structures and a short outlook. Of course, if no one is interested, I would not continue to do that. But if you find this interesting, we would look into arrays and how to do address calculation with arrays. And today we just stored numbers in the fields, but you could also store execution token and addresses in there. And then it's quite easy to build objects with that. So you have fields with execution tokens, and instead of just fetching, you fetch execute. So based on the data structure, you do different things, which could be the foundation of objects. So we can go into that. Or a very nice one is enumeration types. So you want to name the days of the week, for example, because then you can deal with them again for avoiding magic numbers. You can define enumeration types quite easily, and there's also a way to do that. And similar, you can do this by hand, as we saw today, or you can use some definitions that help you in doing so, and then things become much more readable and much more usable. So yeah, thank you very much for listening, and I'm open for questions.
Thank you, Ulrich.
Right.
We are a bit late, 8 minutes past the hour, so I hope we do the questions later.
Okay, no problem. Yeah, we do that.
Bernd, are you ready for your talk?
Yes, I'm ready.
Fantastic. Go ahead, please. Analog computer demonstration.
Okay, yes. First of all, thank you very much for the invitation. I hope you can all hear me. It's a little bit noisy here due to the fans of the analog computer, which is currently up and running. This is a perfect example for a classic analog computer, which I would like to show you before we go on to more modern implementations and applications of analog computers. Maybe some of you have already heard about the notion of an analog computer. The idea is you compute not by programming it with an algorithm, but by basically interconnecting various computing elements with each other, so to create a model for the underlying mathematical problem you want to solve in the first place. So an analog computer is basically a data flow machine, if you would like to call it like that. And a typical analog computer represents values by voltages and currents. The fact that you see a museum piece up and running here should not bring you to the consideration that analog computing is something which belongs to a museum. Analog computing as a computational paradigm has a very bright future. Why? Because analog computing exhibits an incredible amount of parallel computation, much higher than every other computational paradigm. And analog computers are very, very energy efficient. That is, of course, not true for a museum piece like this Electronic Associates EAI 680, but for modern implementations of analog computers, this holds very much true. So an analog computer is basically, as I already said, a collection of computing elements, hundreds, sometimes even thousands. This machine here, the EAI 680, this is the 1967 collection. This is a so-called scale analog computer. Large scale analog computer is this incredibly heavy and big EAI Pacer 700, but this machine is unfortunately still not up and running. I'm working on this since the last 6 years now, and there's no light at the end of the tunnel getting this machine back up and running again. But I can show you a little bit, give you an impression of how to program an analog computer. The most prominent feature of a classic analog computer is this huge patch panel. On this panel are all connections go to computing and computing. And we get a little bit closer. You can see, for example, here a computing element that can be selected to operate as either a summer, which is simple, or, and that is like my friend Chris Giles always said, the real magic behind an analog computer. This computing element can also perform an integration. So an analog computer has computing elements that perform typical algebraic operations such as summing or multiplication, but can also, the basic operation of an analog computer, perform an integration operation. And this makes this type of computer ideally suited to solve dynamic systems, systems which are readily described by systems of coupled differential equations. That's something which is notoriously hard for a digital computer to do, especially when your problem gets bigger. The incredible advantage of an analog computer over a digital machine in this particular field, an analog computer should not be considered being a general purpose machine. An analog computer was and always will be a special purpose machine geared towards the solution of systems of coupled differential equations. But when you have a problem involving such systems of differential equations, an analog computer, especially when it is implemented with modern technology, is something I will talk about in a couple of minutes. An analog computer is sometimes several decades faster and more energy efficient than a digital computer when it comes to this type of problems. Now that you have seen the so-called patch panel, you may wonder, isn't it horribly complicated programming an analog computer? And the answer is no. It is much easier than programming a digital computer. Why? Because when you have a real nasty problem, in every case, you need a mathematical description of your problem. When you have a digital computer, this is only the starting point for developing a program on your digital computer. Then you have to transform your mathematical description of your problem into an algorithm solving the actual problem. This step can be skipped with an analog computer. The mathematical description is basically enough to program an analog computer because you just connect computing elements to each other with the goal to implement an electronic model of the underlying mathematics. So programming an analog computer is incredibly straightforward, and as intimidating as this bunch of wires, and I will show you a more complicated program in a couple of minutes, may look at first sight, it is much more simpler to program than a digital computer. Just the patch panel alone is not enough. Large or medium scale, as they called it, by the way, medium scale, this machine weighs in excess of 1 metric ton. Such a medium scale analog computer also has an operator console where you first of all can set a lot of gates. It also has some digital computing elements which are useful when you have logical decisions to make during a computation. For example, you want to optimize some dynamic problem and you have some restrictions. This would be the ideal application for simple logic gates. For example, if some condition is met, then change some parameter in some differential equation or whatever. And the main operating console is this here, where you can set the computer to the various operation modes. And you see here a digital voltmeter, which is currently connected to some computing element, which is not really part of the setup. Thus, it is spitting out pretty much garbage. And I've prepared a very simple program on this machine. The program you can see here, and you can see only a small fraction to show you, but what this machine is instructed to do by means of this program is it simulates a very simple spaceship, and you have a very simple and not very realistic flight controller, an old joystick. And what you can do is you can accelerate along the longitudinal axis of your spaceship. So you see I can accelerate or decelerate, and I can rotate the spaceship. So it behaves pretty much like a spaceship would in a force-free continuum. And I can now play rocket pilot without risking anything. By the way, this very machine, not this machine, but this type of machines was used by NASA in the 1960s as the basis for the lunar landing simulations. In fact, landing on the moon is so complicated that it required 3 of these pretty big machines just to implement the orbital mechanics for the lunar lander, especially because the moon is a nasty place to land on, because it has all kinds of mass concentrations, so-called mass cons, and you have to take care of your orbital inclination and whatnot. So this machine really made history in the late 1960s during training the astronauts to actually land on the moon. I have a computing element from this particular machine that I can show you. This really large module, which is incredibly heavy, not incredibly heavy, but weighs several kilograms due to its sturdy build. This, in fact, is an integrator. That is an electronic integrator which has several time constants, 4 time constants, and very high precision input resistor networks. That is the very, very high precision integration capacitor bank. And this is the discretely built operational amplifier. So behind this patch panel, you have 150 of these modules. Some modules performing integrations, other whatever. And the connections are made by means of the patch cables to the front of these modules, while on the back of these modules, you have the power supply and the trunk lines and the readout lines and the addressing lines and whatever. So this is a typical example for a classical analog computer. I have a second example to show, and I will switch it off because it's so horribly noisy. Quiet at last. I have another example of a classic analog computer that I can show you. This one, that is also running a toy problem, so to speak. This is a typical German machine. This is roughly 2/3 of the computational power of the EAI 680 you just saw. And this machine, like the EAI machine I showed you, is already fully transistorized. And as big as it is, it only consumes about 500 watts, which is really impressive for a machine dating back to the 1960s. And you see, you have basically the same complement of operating features. You have a big patch panel, and the patch panels can typically be removed when it comes to classic analog computers. So a classic program library for an analog computer installation would consist of a big shelf containing pre-patched patch panels for various problems. You also have an operator console, and here you also have an oscilloscope, and this machine simulates a very, very simple car suspension system. So basically it is a 2-mass spring damper system with a road that is bouncing up and down in a stochastic manner. It is very, very simplified. Typically, the roads should bounce up at the front of the car first and then move to the back of the car. I've skipped all of this just to have something to show visitors of the museum how analog computers are programmed. And as intimidating as this program here might look, it is basically really very simple. About half of the program is required to display the car frame, which is basically just for show. If it were a real problem, you would, for example, plot the accelerations and velocities of the car frame, of the wheels and of the street on a multi-channel strip recorder, and then see if some parameter exceeds, for example, permissible limits for physiological reasons or the like. And I have a really old program that is a real treasure. This program, this is really nasty, and this is part of one of the world's first electronic car simulators. This was used in Germany by the German car manufacturer VW Volkswagen in the early 1970s, and they developed their cars. For example, the Golf 1, a very, very popular car here in Germany back then. The Golf 1 was designed with this program. This program, in fact, is the dynamics of the overall car. The complete car simulator consisted of 3 very big analog computers. So this patch panel is only 1/3 of the overall car simulator system. But I promised you to show you some more modern developments. These are all museum pieces that you can see here. But a couple of friends of mine and we are also developing modern analog computers, and I would like to show you how modern modules for analog computers look like. This, for example, is four-channel integrator module, and you see you have. This is way simpler to patch since it's a little bit more spacey than the traditional machines. You have inputs. These are the circular marked connectors, and you have outputs. And this is one integrator, second one, a third one, and the fourth one. And the integrators basically are implemented using modern surface-mounted components and can also be adjusted. And this is the basis of a modern fully modular analog computer, of which we already sold some machines. Interestingly enough, it started as a hobby project and ended up with some of our machines now running in as far as in Japan. And we are currently working on the next generation. I've also brought you one of the prototype boards for the next generation analog computer. And this prototype board shows you the next generation of computing elements. We have chosen to use DIMM style printed circuit boards. This is a prototyping board, so there are no components installed on it as of now. And these modules can plug in into the backplane of one of our modern analog computers. And the really interesting thing is we are currently working on a so-called auto patch feature, which means that we can get finally rid of this mess of spaghetti wires and have basically very, very large stacked crossbar couplers, which are controlled by an attached digital computer. And this is now where the idea of FORTH comes into play. Wait a moment, I just have to go upstairs to show you how the current state of affairs looks like. So here you have, for example, one of our modern analog computers. And this, by the way, is an interesting program we are currently writing a paper about. That is the quantum physical simulation of a water molecule. Sounds ridiculous, but it's pretty interesting, to be honest, since in pharmacological research and biological research, the behavior of water on a molecular level is really interesting and is something where lots of computing power is spent on. And this machine has a unique feature. This has, you can see here, a hybrid controller. You see the blue USB cable, and this hybrid computer attaches the analog computer to a digital computer. So the digital computer can fully control the operation of the analog computer, and the analog computer acts as a numerical coprocessor, but not working in binary format, but using voltages or current to represent values. And one of the problems you encounter when you couple a digital computer with an analog computer is the digital computer is way too slow for the analog machine. Even communication, communication over USB is very, very slow. But we already have tried attaching an analog computer to a digital computer, i.e. analog and digital input-output cards, and even this is too slow. Even using a real-time Linux optimized kernel has way too slow interrupt response times to efficiently use the analog computer. Typical solution times for a very complicated system of differential equations on the analog computer are in the ballpark of about 10 to 100 microseconds as at most. So if you spend 100 microseconds for interrupt processing, the analog computer has already finished its computation. And this problem gets worse with the next generation of analog computers. We have finally, at least I hope so, managed to secure funding for our new company, which is devoted to developing an analog computer on chip. And with the analog computer on chip, we not only get rid of all the cabling and get the form factor much smaller, it also becomes much, much faster. And we are confident that we will be able to solve basically as complicated systems of differential equations as you can think of at a maximum 100 nanoseconds. So the analog computer will have finished its computation before the digital computer has even filled its cache. And a central problem is how to control the analog computer without slowing it down so that it becomes unbearable. And the solution will be, I'm pretty sure, will be a local digital processor, which will be part of the analog computer on chip. It's basically a mixed signal chip, a small RISC kernel or the like. And we will, at least we plan to do so, run a FORTH interpreter on this embedded processor, which then controls the analog computer. So the host computer will not communicate directly with the analog computer. That's way too slow, however you do it. Even PCIe is too slow. The PCIe latency times just kill you if you have a lot of communications, which is not based on blocks of data, but on single data values. So the plan is that the host computer will communicate with an embedded RISC processor or FORTH processor, which runs a FORTH interpreter. And the overall control of the analog computer, when to stop, when to start, which digital potentiometer set to which value, will then be done in a very small and very, very fast FORTH program. So this is where both worlds, my beloved analog computers and our beloved FORTH world, finally come together. So I hope that I can show you next year or so the first attempt of a hybrid controller, which takes control of an analog computer based on a FORTH system underneath its HUD. So that is basically all I have to tell and show you about analog computers. You see there are lots of analog computers here, but the next step for us is going towards an on-chip integration, and we are planning to use a 160 nanometer process, which is really huge compared by standard. But if you do analog electronics on the chip, you typically do not want 2 nanometer transistors, but will prefer 160 nanometer transistors, since it's easier to match the characteristics on the chip, and it gives you a much higher core supply voltage, which is very beneficial to increase the precision of the analog computer. So thank you very much for your interest. And that's the end of my quick talk about analog computing. Have a wonderful weekend.
Wonderful, Bernd.
Great, thank you very much.
Thank you very much.
Fantastic.
Just a remark I can think of, maybe it's good, or maybe you even have already contact to the people at CERN or at the DESY in Hamburg.
Yes, I had contact. The interesting thing is the accelerator at DESY in Hamburg, they actually used analog computers in the 70s and 80s to simulate the beam control magnets. Unfortunately, all of their analog equipment has long since been scrapped. And last year in February, I was even invited from CERN to give a lecture at CERN about analog computing, and they never did anything much with analog computers, but they are very interested in our proposed analog computer on a chip, especially things like beam simulation. Right.
But they are also facing this issue that they have the experiments and they need to get the data that is collected away as fast as possible. So maybe you can look at the solutions they have to communicate in high speed.
Yeah, that is one of the big application areas of analog computing for the 21st century: edge computing, pre-processing of loads of external data, for example, spectral analysis and whatever, to offload this from the digital machine, which then does the fine processing of data. Yes, also applications in artificial intelligence are very, very promising and interesting.
I'm interested in how many bits you want to use of are necessary to control such an analog machine from the Linux.
That depends on the size of the analog machine. For example, if you need a coefficient in the classical analog computer, you have a manual potentiometer with a resolution of about 1 in 1,000. So this corresponds to 10 bits for a single parameter. If you have a complex computation with 500 parameters, so that's already 5 kilobits. Then you have to control your crossbar switches, which also amounts to several hundred bits at least, maybe some kilobits. So we are talking about many, many kilobits to set up a complete analog computer run. But when it is set up, it's incredibly fast. And typically applications are, for example, parameter variation studies, when you have systems of differential equations where you know the structure of the equation, but not the coefficients. And then you do basically a Monte Carlo simulation looking through your n-dimensional parameter space.
Okay, but that means that you are, or that the Linux computer is not well suited, because it can easily put out a 32-bit number in approximately a nanosecond.
Yes and
over
no.
the address bus.
Yeah, yes and no. If you have a look at modern PCIe implementations, it's basically a serial bus. So you need deserializers anyway. And you have latencies in the range of several nanoseconds just on the PCIe bus. Then you have latencies in the micro or even millisecond range for interrupt handling on the Linux side. That's a real problem. The reaction time is too slow. Setting up the analog computer is one thing, but reacting to an event generated by the analog computer is a whole other problem. If you have, for example, a complex simulation, for example, of a nuclear power plant, something I'm currently working on as a pet project, and you have to react from the digital computer to, for example, a power excursion in your simulation. If your simulation runs maybe 10,000 times faster than real time, you have only 100 nanoseconds or the like to react to this and change a parameter on the analog computer side. So the interrupt latency is basically what makes interfacing an analog computer to a digital machine really difficult, not the actual transfer of parameters.
Okay, I get better idea.
Sorry, can you unshare your screen, please? Perfect.
Dimitri had a question.
Yeah, hello. My question is, what is the hardest part of programming an analog computer?
The basic programming can be learned in a day. The hardest part is scaling. The problem is the advantage and problem in one is that you represent your values as voltages or currents. So you don't have an equivalent of a floating point number. You basically have something like a fixed point number, and you have an interval of permissible values which ranges from -1 to +1, whatever -1 and +1 is in the actual machine. So you have to scale your problem such that you never exceed this interval of computing variables, and also make sure that you make as good use of this interval as possible. And that is really, really hard when your problem gets harder. But we are also working on a system which will permit the machine to perform an auto scale. So you basically will program only the structure of your program, and the analog computer and the digital computer will work in tandem. So whenever the analog computer experiences an overload, a variable which is not inside the permissible interval of values, then it will generate an interrupt, and the digital computer will then rescale this part of the analog computer program without manual intervention. And so you will have some kind of a ping pong between the analog computer and the digital computer. So in the future, I'm pretty sure that scaling is nothing to worry about, but at the moment, scaling can be really hard.
John has a question. John, please, go ahead.
Thanks. Just a quick question. I was just curious about when you're miniaturizing an analog computer.
Yes.
What sort of implications happen as you get smaller? You're going to have things like interference and other limiting factors. Is that a concern as you get the circuits more?
There are many concerns.
Miniaturized?
Yes, there are many concerns. One concern is the basic structural size of the elements. You cannot get too small, and 160 nanometers, for example, is already pretty small for a high precision analog circuit. That's the first problem. The second problem is you need an on-chip crossbar switch consisting of tens or hundreds of thousands of FET switches, which can be configured to interconnect the various computing elements with each other. These FET switches are not perfect. When they are switched on, their resistance is not zero as it should be. When they are switched off, their resistance is not infinitely large, which it should be. So that already poses a certain problem. Then you have to have digital parts and analog parts. For example, every coefficient is basically a multiplying digital analog converter. So you have various voltages on your chip, which makes design pretty complicated. You have two ground systems, which you have to take care of. And a real problem which we are currently working on is interfacing to the outside world. As long as you are on chip, things are not simple, but at least pretty straightforward. But if you have to go outside of your chip, things become really nasty, starting at ESD protection and getting all kinds of electromagnetic interference and the like. That is really complicated. We are already at least talking with another research group, and they are working with on-chip photonics. And the idea is maybe we can implement an optical link between our analog computers on chip, but that's in the very far future. Our current plan is to have first silicon in our hands in about 1.5 or 2 years from now on as a technology demonstrator, and from there on start to develop more specialized analog computers on chip for certain applications like artificial neural networks or the like.
Okay, one moment, please. I suggest, I see many rising hands in the meeting. Bernd, can you unshare your screen, please?
Did I share? I have not even shared.
No, it's
my
not sharing.
screen.
I think you, Peter. We can.
Okay,
He's
okay,
not sharing.
no problem. What I suggest for the questions, Bernd, have you time for the coffee break to answer more questions?
When will the coffee break happen?
In an hour and a half, probably, or 2 hours.
That's already dinner time here. My wife won't be too happy about this, I think. But if you like, you could collect all of you the questions and send them to me by mail, and I will write a long reply and send it to you, Peter, for distribution. What about this?
Perfect, perfect.
Yeah.
I agree.
If we can put it on the Facebook group, actually, that would be good.
Yes, yes.
Mm.
Okay. Just collect your questions and I will answer them and post the answers in the Facebook group.
Yes, yes. Okay, we continue, Bernd. This is fantastic. You see how many people, how many people are interested. It's fantastic.
Yeah, great.
Thank you so much
again. Yeah.
Have a wonderful weekend. Bye.
Bye-bye. Now we have Pablo Reda will show us a FORTH computer inside the ESP32. How are you doing, Pablo?
Hi, I'm here. I'm sharing the screen. You see?
That works.
Perfect.
Well,
yes.
This is the attempt to make a FORTH computer with the ESP32 microcontroller, similar to Spectrum or Jupyter Ace, but with R3 language. The interface with the screen and the keyboard is made with a library, and this library generates the VGA signal and get the keyboard and mouse too, and sound is possible. This is my connection of the my ESP32. The implementation. Well, I implement a virtual machine in the microcontroller. Is a bytecode interpreter, and this virtual machine execute machine 4. Machine 4 is an assembly for the FORTH language. The difference is you have a call instruction, explicit call instruction, a jump conditional, and literal. The main loop of the virtual machine is a big jump table. I show the this is the sorry for the C code. This is the main interpreter loop. The loop is only get the bytecode from the memory. IP is the instruction pointer, and OP is the operation in this memory. It's only a big switch statement executing every code and go to the next instruction. It's similar to E4 for ESP32. You see all the basic variables are in registers or intend to compile to registers, and then this a very fast interpreter. It's only a big case. You know, the case statement is a lie. The compiler can make the assembly for two types of case. When the options are numeric consecutive and full, is a jump is a on go to the antique on go to instruction, and then this transform in a array of memory, and jump with this array to the site where are these instructions. For example, this is add instruction. Yes, the toast is top of stacks, and add toast with the content of the next of stack, and async to do the toast, and reduce the stack in one cell. This is a code for ESP32, but here is the same thing, a virtual machine in the Erlt language. For example, this is a plus instruction, and the array of bien.
Pablo, you're
registers,
fading away,
and the language have 2 registers more for traverse memory.
It's now working again.
Again?
As soon as I said this, it's working again.
Okay. Well, the compiler. The compiler transforms the string in bytecodes and data. The compiler is separated from the virtual machine. In this language, the behavior of compiler is guided for prefix. For example, hash prefix define data, colon prefix define code, single quotes define or express address for data for code, pipe make the comment until the end of line, caret are then included, string with defined with this character, and dollar and percent defined base. The compiler in the string and generate every bytecode for execution. Now, here you can see the prefix, of the word, separated by a space and trim the space, and this all the compiler, the main loop. If have a prefix is go to the piece of code to resolver, or try to detect if a number is a core word, is a word defined, or in case to the ASP32, add a new type of word for system for this experiment. About R3 language, the idea of R3 language is remove the compiler manipulation from code. Classic 4 have immediate, here, comma, create, do's. Color 4 have here, comma, and cyan words. Cyan words have is word who put the code of the word in the place when you name a cyan word. It's like inline, and R3 have none of this mechanism. Use explicit prefix instead color. Really, color 4 have this prefix in the codification of a word, but I do explicitly. And I need rethink the control flow, because in FORTH you make the control flow words with this compiler manipulation words, and I not have in this language.
I can't hear Pablo anymore.
Pablo, you have lost your connection.
Tell me.
I can try to minimize his video, so maybe that helps. Oh, he's gone. Looked like we lost him. Maybe he reconnects, and then we can suggest that he does not use his video.
He can come back later, Ulrich, and we go on with Greg.
Okay, right. So yeah, I was so much into R3 right now, but of course we can do that. That's probably a good thing. So we continue with Greg Schmidt and see if Pablo returns, how we deal with that. So Greg, are you with us?
Yes, I'm here. Can everybody hear me?
I can hear you at least. And
Okay.
Hey, Greg, you will present a family problem here.
I'm sorry?
You will present a family problem. You have a family problem here.
Yeah, maybe we will hear. So the stage is yours. So you can share your screen and we learn about what your talk is about.
Okay. Everybody can see my slides?
Not yet.
Oh, okay. I should be sharing. Whoops. Okay. Hold on.
Well, my joke was, this is not forced. This is a family problem of Greg. He had a problem with his sister and his cousins.
Looks like so.
Okay. Right. My mouse is.
I am here again. I am here again. Sorry for my English and for my cut on internet.
Yeah, Peter, how do we want to deal with that?
Let's talk, Greg. Greg, can you wait a minute, or can you prepare your screens and etc. and Pablo continues?
Yeah.
Yeah, that's fine.
Okay, that would be great. Pablo, my suggestion would be that you switch off your video to use all the bandwidth for your voice and the presentation. And so then you can continue, please show your slides again, and then hopefully it works.
I continue?
You can continue. And
yes,
if you switch off your camera, then that would be good. Or I can do it for you. All right.
You can just see me. You can see me.
Just go ahead.
Okay. Well, this language can enable deep optimization when compiled, dead code elimination, automatic inline, discover constant in variables, and reorder the code. This is a computer implementation, no SPI implementation. For example, this is a code, and I do the analysis of the code, and I can execute it step by step a word. And see the screen how is drawing. For example, here and here. Yes, this is made with the R3 code of VM virtual machine implementation and compiler implementation. I know show the virtual machine in R3. Yes, this is the virtual machine, and this is the compiler in R3. The same of this is this in R3. The same with the preface guided the compilation. Another difference of FORTH is separate memory in data and code. Dictionary can be discarded when finished compiler, because this separation something is a better performance. In classic FORTH, I have this. We have this structure of memory with a dictionary entry, a code, another dictionary entry, a data, and so on. And R3, this three type of data is made separated. Another consequence of this is when this is an interpreter code, and if compile this code, this generate two files. The data assembly it is Intel assembly. This is data, and this is code of the R3 program. Here, this is the work compiled, and this is the assembly generated. And this is a compiler version of the same program. I show you this for see how is generating the code. Another things about this language are have null terminated string, have file stem block, not using floating point number, is only a frame buffer, no have consoles, but in SP32 use a console experiment for memory problem, and have a rigid interface with operating system. Is easy to convert to other operating system, but is less flexible. No library can be attached in runtime, like SP32. And for use this experiment, try to add interactive mode, but it's not comfort for me, and make a load, edit, run cycle. Editor is made in R3, not C, and perhaps in future only leave the virtual machine on the SP32 and make an interface for transferring the bytecode to external world, and the compiler no need to stay in the microcontroller. Well, this is the machine. I reset the computer. Have the word directory. This is a flash memory in this is the flash memory in the microcontroller. Can load a program, for example, colors, edit the program, see the dictionary, and execute. I can edit again, change the rows, exit, and re-execute. The editor is in the flash memory and need to be loaded here. This is the editor in Erlt who reside in the flash memory of the microcontroller. And the microcontroller, when edit a program, load this file, compile and run this file, and maintain the file name of the program for reload when exit the editor. And the load snake, another example. That's it. It's all.
Right. Thank you very much. Yeah, very interesting, very interesting. I was looking forward to hear about that. I read this on a little bit on your GitHub page, and yeah, to see it live, that's really astonishing. Yeah, great.
Very nice, Pablo. Very nice. Good.
Thank you.
Now with Greg. Sorry, Greg.
Okay, let's get started. I'm going ahead and sharing, so hopefully everybody can see this.
Ah, this works.
Okay, let me get my presentation going. Okay, how does that look?
That works great.
Okay, great. So what this is about, this is really just a story I'd like to tell that I thought people might be interested in. It relates back early into my career, some discoveries I made related to threaded code. So not directly related to Forth, but only in the sense of threaded code is the foundation for Forth. So the title of this presentation is rather strange, turning cousins into sisters, but hopefully it'll become evident what that's about. But essentially this relates to sort of smoothing or glossing over hardware differences through the use of threaded code. And this title is not actually my own. It comes from this somewhat obscure book, Computer Engineering. I'm sure a lot of you probably recall Digital Equipment Corporation or DEC computers. They were big in the late 60s, 70s, and 80s. And in the early part of my career, I worked almost exclusively with DEC computers. But this book describes a lot of the hardware and software architecture of DEC computing machinery. It's written by an engineer called Gordon Bell, who was an early employee of DEC, and I think he does have some fame in, as a computer pioneer. This book, by the way, I believe it's in the public domain. I don't have a link. It's available as a PDF. If you search for it, if you're interested, I'm sure you can find it and download it. But one of the chapters in this book is named "Turning Cousins into Sisters," and I thought that there were some interesting revelations behind that we can talk about. So I guess think of this as just a story I'd like to tell, a parable. So grab a beer, whatever, and let's get started. So Fortran. So I'm sure many of you know Fortran was a language that was developed in the late 50s. It stands for Formula Translation. It was, I think, one of the first high-level languages that provided a level of abstraction. Prior to that, there was low-level languages. Assembly language was common back then. But Fortran enabled scientific programming, and so came of age and had a lot of applications, and allowed a lot of scientists to use computers, and hence DEC wanted to develop their own Fortran compiler for obvious reasons. They wanted to bring it to market quickly, and even if they may perhaps sacrificed a little bit of performance. The fundamental design strategy was really to determine the structure of the executing code, the runtime environment. They were leery of machine code due to size of compiled code. They didn't want an interpreter due to the overhead and bloat of an interpreter, right? Because you may have functions that are not used by every program. So they investigated threaded code. So neither a compiler nor interpreter, but threaded code, a kind of combination of maybe the best of both. So the PDP-11 architecture had a very nice orthogonal architecture, if you're familiar with it. But just basically, it had a very nice instruction set. It had 8 registers, most of which were general purpose. The program counter was actually register 7, so it was dedicated for that. And register 6 is the hardware stack pointer. But all of the instructions could operate on all the registers. So you could do math on the program counter or the stack pointer. In their implementation of threaded code, they chose to use register 4 as the next address pointer, which we're all familiar with in Forth as the IP pointer. And the jump instruction, an indirect auto increment jump instruction, essentially could implement the next function that we're familiar with in Forth to essentially go to the next, execute the next word. And this jump occupies a single word of memory, so it's rather efficient. So here's an example, or here's a very simple example that's missing the code, but this would be the assembly language for adding a real value. So you would have the code that does that. This would be the address of that word, if you will. And this would effectively be the single instruction which functions as next to jump to the next word once you entered threaded code mode. So some examples of words is, I don't know that they call them words, I'm calling them words, but if you wanted to push a variable onto the stack, this would be the assembly code for doing that, or effectively the word. The pop would be implemented simply as this. So if you had a Fortran assignment statement, and these are both integer variables, the generated code would be push variable, and it would be pushing the value of j. So this is the address of the J integer, and then pop that value into and store it in the address of the I variable. So, you know, a very simple statement like this might be translated into threaded code and look like this right here. So to enter threaded code, there was this word, if you will, called POLSH. I think that must be short for Polish because of, you know, Polish notation, right? Stack-oriented code. But this is what essentially gets you into threaded code. So on your stack, you would have the basically the first word of your threaded code list, and that would be going into the instruction pointer, which I mentioned was R4, and then we just call next. And then to exit threaded code is very simple. You just follow your list of words, if you will, with the address of the next statement, and that causes next to basically execute the code following you know, that threaded code list of words, so you're back into normal code. So here's an example here's a little bit more complex example. In Fortran, if some of you may remember, there was what's called a computed goto. And basically in Fortran, you have line numbers. So a computed goto basically says, go to one of these line numbers, and this list can be, you know, a variable length. It doesn't have to be 3, based on the value of I. So if I is, don't remember if it was 1 based or 0 based in Fortran, but at any rate, based on the value of I, let's say if it was 0, we'll go to statement 100. If it's 1, we'll go to 200, and 2, we'll go to 300. So the threaded code implementation of this actually somewhat resembles the actual statement. So we have this word called computed goto, and in memory following that is the value I. Looks like they also included a count of the following address labels, which these would translate, these statement line numbers would translate to addresses in the generated assembly code. And then you'd have that list. And then the computed goto would fetch the value of the index. It looks like it's checking to see if it's positive. And it's comparing it to make sure that it's within the label count. And I guess it is 0 based because it's just doing a shift here. So it's multiplying it by 2 to get the offset, word offset into the table, fetching the target label and then jumping to that. But as an observation, notice that there's also this, as I mentioned before, there's this error handling code. So I'll talk a little bit about the significance of that later. But the point of this is that we've essentially created a stack-oriented Fortran virtual machine, and the idea is that the threaded code can somewhat resemble the actual constructs that we see in Fortran. Now, what you may recall from the previous slide where I had the assignment, the I equals J, you might have looked at that and said, well, there's 4 addresses just to do an assignment. Well, that isn't very memory efficient, is it? So what they did was the compiler would actually generate program-specific push routines. And so if the same value, if an integer or a particular constant or a variable was used 3 or more places in the program, they would generate specific push routines for those variables. And since Fortran also supports the notion of a complex variable with a real and an imaginary component. That occupies a little bit more space. And they decided that 5 uses of that was the break-even point. So if there were 5 or more uses of a complex variable, of the same complex variable, they would generate specific push routines. And so this first one is just a specific to the variable I. So this is a push routine. This would actually be generated, and it very specifically pushes the value of I into the stack and calls next. This is an example of a complex which has, 4 16-bit words as its representation. So it basically pushes the address +8 because it's pushing it in reverse order. So it's actually going to the end of the definition of that, where that complex value is stored, and pushing it onto the stack and then calling next. So I don't know if you can read this, it's a little bit small, but there's some examples here where we're incrementing a integer count, and then we're doing some mixed math here. And this would be the code that's generated. And then these would be the specific push routines. And then following that would be the allocation. So we can see we have, for this complex, we have two words of data. Real, this float directive basically, I believe, creates 2 words. And we have our integer, simple integer, 1-word declarations above that. But then these are the specific push routines. So here's for the integer k, we just, similar to what we saw here for I, we just push the value. Here's a literal, essentially the value of 1. You could see that being used multiple places in a program. So it created a very specific push routine for that. A, I believe, is the float. And another optimization they did is the actual push of the floating point constants was common code. So you can see these floating point values here are all sharing this common push code here. And this was all generated by the compiler. And I actually remember when I was in college, we had a PDP-11, and I was doing some Fortran, and there was an option to actually see the listing file that it was generating, the assembly listing. And I remember looking at this and really not knowing what it was, and being somewhat fascinated by it at the time. But certainly after having read, found it in this book, it was rather fascinating for me to see what they were actually doing. So one aspect of the PDP-11 machines was that the hardware evolved over time, and they had different options for floating point. So, well, actually for math in general. So they had the basic PDP-11s all had all their math was done in software. Then they added what they called EAE, which was integer multiply and division. Whoops, I actually accidentally clicked to the next slide. Sorry about that. Yeah, this says the same thing. I'm not sure. There might have been some other variations here that I didn't quite catch, but they had EAE, EIS, FIS, which had single precision floating point done in hardware, in addition to the integer multiply and divide. And FP11 had some similar capabilities, but all of these resulted in some subtle differences in the code. And because the implementation of all of these threaded code words, if you will, actually were in a separate runtime library that could be linked, the evolution of this software could be done without really having to change the compiler. Basically, they just changed the runtime library. And so on the right here in this box, the add real basically became conditionalized. So these are conditional assembly directives, and based on whichever one you defined, in your for the version of your runtime library that you wanted to compile, you could compile your runtime library to target one of these architectures. So that made it very nice. They could evolve their floating point and integer hardware capabilities in their CPUs without having to really change the compiler. Shifting gears a little bit, during the early 80s, early on in my career, I worked in the industrial and process control area. And it was common back then for mini computers to be used, and DEC computers were fairly prominent in the industrial control market. So I worked for a company that had a product called CRISP. And yeah, the name CRISP was derived from the founders of the company, a guy by the name of Copeland, another guy by the name of Roland, and I think they came up with industrial systems processing, for that acronym. But we had a language, we had a compiler called the CRISP compiler, and it was intended for industrial control, for batch, continuous, sequential. Those are typical areas of industrial control that that involve different types of control, but the language was intended to support all of those segments. It was essentially a Boolean language which had some mathematical expressions, and it had built in, or it had functions that could be called. The language would allow you to read from process inputs, which would typically be from IO cards or input cards, store those values in internal values, manipulate them, and then you could write based on your calculations. You would write to the outputs. So you were doing, implementing control loops and such. The language had built-in parameterized functions that could be called. And these functions, I found out, resided in a runtime library that was then linked into the user's program. So on the right here, you see all these let statements. This is the Boolean part that I was referring to. And then we have this parameterized function called control, which has these control parameters. This is essentially a PID loop. So these two control statements are doing closed loop analog control. So there's they're reading an analog input. It's probably being scaled. It's being fed into this control loop, and it's maybe trying to maintain a temperature set point and then writing to an analog output. So that's the gist of the CRISP language. But then one day, I sort of stumbled upon something. We had a small room that served as a library, and I don't think I've ever seen anyone enter that room, or if I did see somebody, that maybe they were just sitting at a table doing some work. But the room had shelves of listings that the founders had worked on in the past. And I've never saw anyone pull one of those listings and bother to look at them. So I decided, being the curious person that I am, I grabbed one of these listings and started looking through it. And I was surprised to see that these were programs that were written for customer systems and directly written in assembly language. They started with the enter Polish mode, and it appeared to be handwritten and what resembled code generated by what I was familiar with from the DEC Fortran compiler. And not having been familiar with the internals of the compiler, I found that it produced somewhat similar style code that I had seen before in the DEC compiler. But in this case, this was done strictly, manually. So what I found interesting was that that the founders stumbled upon threaded code as a means of a style of writing assembly language that was very efficient and applicable to the control problems that they were solving. And that I think what happened was then they later developed this CRISP compiler that sort of automated the generation of that. By the way, I did happen to find a copy of the book, Computer Engineering, on the shelf. So I never actually found out the exact history of that, but I suspect that it was inspired perhaps by that chapter in the book that I'm referring to. And then at some point later, I was given the task, we were actually migrating our compiler from the PDP-11. Many of you may remember the VAX, which was really intended to be the successor to that. So I was actually given the task of migrating the runtime library from the PDP-11 version to the VAX version. And one of the things, and I still had this lying around. I mean, the company is long gone, so none of this is proprietary anymore. But I had to. One of the things I was tasked with was taking the PID control statement, which was implemented, as you can see in this, threaded code implementation, and translating that into a VAX specific implementation. So this actually gives you a sense of what this code looked like in the runtime library. Now, all these comments on the right were added by me. These were my annotations to try to reverse engineer what this was doing, because I don't think I was given much at the time, but I was able to reverse engineering it from looking at this. But here is an example of threaded code that was used to implement one of these library functions. So I found that was rather interesting. So anyway, I'll end with just some of my takeaways with threaded code in general. I think it can lead to compact and memory efficient implementations, which of course was more of a concern back in the early to mid 80s than it was now. I'm also struck by how well it can be adapted to the problem space. And we see this with Forth, right? In this case, we saw that it maps well to Fortran constructs, as we saw with the computed goto. We can see an almost, one-to-one mapping between, a high-level construct and the threaded code equivalent. The other nice thing about it is, as I mentioned, it supports a compiler front end that doesn't have to change as the virtual machine, if you will, itself improves by creating abstractions, being the words, and separating them from the particular implementation. In the computed goto example, I mentioned the error handling code. Well, that's an example of something that doesn't have to be there. So I don't know if they did this or not, but you could certainly have a debug version of that runtime library that compiles in that range checking code. And then once you're satisfied that your program is working properly, you could compile against the more efficient release version that doesn't do those checks. So, it gives you that ability as well. And, the next bullet, what I saw was it allowed us to create a specialized language for solving problems within a specific domain. So in the process control environment, the threaded code again mirrors the high-level language very well. And finally, in relation to Forth, I think that Forth and Forth-like languages really encourage and embody these principles. So so that was it. So I hope you found it interesting, but it was just something that relates back to my early career experience that I found rather fascinating. And so.
Right. Thank you very much for this view into the past. And
A little bit of
hopefully we can take our lessons for today and for the future from this. Great.
Great, Greg. We need you and share the screen, please.
Sure.
Thank you very much.
Okay.
Yeah, Greg, that's a nice talk. Yeah.
Thank
I
you.
think that, you know, the PDP-11 architecture was really the best architecture developed ever. You know, I was very sad to see it went away. I was hoping that, you know, Motorola 68,000 basically emulate PDP-11, but it just failed against Intel. You know, it's very sad to say that a very poor architecture took over the best architecture in computing.
I agree with that sentiment completely. It was really a thing of beauty. I mean, it was a very orthogonal, elegant instruction set, very easy to learn, very regular, uniform, and you know, when I saw the VAX, learned the VAX instruction set, it was you know, I think it's called a CISC complex instruction set. You know, it wasn't quite the same, and you know, I share your observations with Motorola versus Intel. I always preferred the 68, you know, 1000 to the Intel 8080X architecture. I think maybe there was some inspiration there.
Super, Greg. We need to continue with the next participant, please. This is Joe Connor with the Creole in Visual Basic 6. Okay?
I'm ready.
Yeah, great.
Going to share my screen.
That works.
Okay. So let me start the slideshow. Okay.
Fine.
All right. So I've built versions of Forth, which I call Creole Forth, in several different languages, such as Delphi, Python, JavaScript. Why build it for VB6? In this case, because somebody asked for it. In January of this year, Peter put me in touch with Buzz Ross. Buzz has a background in Forth for embedded systems, but also has done a lot of development work using Visual Basic. So he's interested in combining the strengths of both languages.
Joe, shortly interruption. We see your presenter slides, so the preview that the presenter normally sees, but not the main slide. So maybe you can switch the view.
Okay, let me see if I can do that.
I see a slide.
Yeah, but you don't see it in the full screen.
Right? Exactly.
I think it might be in display settings at the top of the window.
Okay. There's a optimize for video clip. I could try that. How does that look?
Oh, that's
good. Go to display settings.
Where's the slide swapping?
It's at the top, just to the right of the, above and to the right of the clock. If you look above your slide, there's a clock. And then to the right of, and above of that is display settings.
Okay. All right, how's that?
Yeah, that's great.
Okay. All right, back to where I was before. All right, I was asked to put together a version of Forth by Buzz Ross, and this short presentation will summarize my work on building a version of Forth for VB6. It is similar in structure to other versions of Forth I built for my own use. I have a version for Excel, believe it or not, which is somewhat similar. The design, it's partitioned into the following VB class files: abspect.cls, reserved for application-specific primitives; ArrayList.cls, used as a basis for the stacks; CompileInfo CLS, it's a container used to help build a high-level definition; Compiler CLS, it's a colon compiler defining and compiling definitions; CorePrim CLS, it's code for core primitives such as dupe, swap, rot, minus rot, and basic math; Creole Forth Bundle CLS, it builds a table of primitives and high-level definitions. You can have several instances of a Creole Forth bundle with a separate dictionary and other data structures. Creole Word CLS, it defines a Creole Forth word. Global Simple Props CLS, it's a generic object that all primitives take as a parameter. It has the stacks and other globally available data structures, and has push and pop. Interpreter CLS, this is the outer interpreter. Do colon is its name in the vocabulary words. Logic op CLS, logical operatives, less than, greater than, etc. Loop info CLS, container for do loop iteration, and return lock CLS, container for return stack information. Creating words. All words are based on the Creole word object. They come in two forms: primitives, you write code in VB, then reference with the build primitive method. High-level definitions are generally built with the colon compiler. Create does pair is available too. They make use of the parameter field, while primitives generally do not. So this is an example in the core prims module what a primitive definition would look like. So I have this, always have the stack comment. And then I define the function. So it takes the global simple props as a parameter. Whoops. And pops them off the stack, adds numbers, pushes them back on the stack. After setting up the core prims module, you would add a dictionary entry in Creole Forth Bundle CLS with the build primitive method. So there's always, creating a primitive is always a two-step process, defining it in code, and then calling the build primitive method, which puts it in the dictionary. High-level definitions. I have a build high-level subroutine, which you just put in your colon definition and an optional comment. The colon compiler, a bit unusual design, has no state variable. Immediate words are all in the immediate vocabulary. Compilation begins when immediate is pushed onto the vocabulary stack. This means immediate words are always first in the search order during the compilation. When compilation is terminated, the immediate vocabulary is popped off the vocabulary stack. This prevents the vocabulary from being accessible when not compiling. Is it usable in Microsoft Office? yes, you can just import the listed CLS files and make sure that the Microsoft scripting runtime is referenced in tools references. There is an example of this in my GitHub repository. If you use it with Excel, primitives like these, they don't react well when placed at the beginning of Excel cells. Because of this, it may be advisable to give them substitute names such as n plus, n minus, n star, n slash, and change the logical operators to their alphanumeric equivalents. Proof of concept, I have a demo application in Excel. So these are the steps I used in building it. Imported the class files into the spreadsheet. I changed the names, as I mentioned before, of the arithmetic and logical operatives to be more compatible with using an Excel cell as a command line. So you don't absolutely have to do that. I just recommend it. If you don't do it, then I would recommend that you start anything that you put in an Excel cell with a single quote, so it'll be properly interpreted. So you do the same with the logical primitives. Then you write an interfacing macro or macros. Write any other necessary primitives or high-level definitions. Application-specific primitives can go in the AppSpec class. So I'm going to go to a small application that I built.
I think your
Okay, I got
application might be
to.
grayed out.
All right, just a moment. Okay, I'm going to end the slideshow, and then I'm going to go to my test application. So can you see my spreadsheet?
I think you might only be presenting PowerPoint. Maybe try presenting your whole screen.
Okay. All right. I'm going to stop the share.
Now it's much better, Joe.
Okay. All right, let me try and share again. All right, can you see my application?
Yes.
Okay, great. Okay, this is what I call a poor man's user interface. So I built a bunch of applications like this in my workplace. So very simple. Instead of building the widgets you use for a VB or VBA user interface, you just put it on a spreadsheet and you run the code on it. So I've run the X. I'm going to be running the hello primitive. So comes up. Next one is vlist. That lists the definitions in this spreadsheet, in this worksheet. Whoops. Okay, so far, you see 82 definitions in this version of Creole Forth. All right, vocabulary I know is a little bit small compared to most Forths. So I'm going to skip past the next one, go into do looping. So 3H is a high level definition. So all it does is say the hello primitive 3 times. Let's see if it does that. Yes, it does. Okay. The final is, the description is Viet flashcards. I'm making some effort to learn Vietnamese because my wife is from Vietnam. And I often, what I do is I have flashcards that I import into a spreadsheet, and then I import into a memory system like SuperMemo. All right, which is it's kind of a flashcard system that you use to retain information in long-term memory. So takes a minute. Okay, so what it does is it takes the flashcards and it puts them in a properly formatted form. It's very simple. You have to have a Q and an A, and then I would have to copy it into Notepad and then save it directly. Saving it directly to a file in Excel seems to mangle the special character set of Vietnamese, but that's not all that inconvenient. So are there any questions?
So thank you very much.
Okay, my pleasure.
Other questions?
No questions? Okay, no problem.
Very good. Thank you, Joe.
Okay. Stopping sharing.
So
we have a request. Do you want? Sorry, Ulrich.
Oh, go ahead. Yeah. Yeah, I would like to ask Anton Erlt to talk a little bit about Euroforth, and he said he has an announcement to make.
So thank you. Yeah, I want to share my screen. And this looks correct. But it isn't. Well, anyway, so you can see all news about Euroforth if you go to www.euroforth.org. And there you find first our new mailing list, which is still a little bit shaky, but it's getting worked out because the old mailing list from Yahoo doesn't work anymore. And you also find a link to our 2021 version. And it will be held in Rome or online, depending on the Corona situation. And the main reason why I want to make this announcement is because of the call for paper is now online, and the deadline for academic stream papers is July the 2nd. So if you want to get a refereed paper, you should submit the paper by July 2nd. if you can also do non-refereed papers, then the deadline is September the 1st. And that's what I wanted to announce.
Okay, thank you very much. So it's as a long-term attendee of Euroforth and organized this in 2019, I can only encourage you to have a look at the old conferences and consider to join us. Right, thank you very much, Anton, for the announcement. So let's proceed. And if I remember the schedule correctly, Bill Ragsdale is our next speaker. Is that right? And
we will resolve an enigma here, Ulrich.
Yeah, the enigma of FORTH. Yeah, and we don't want to go into any historical things on comments on that. So I appreciate that Alan Turing did this great work on deciphering the Enigma. And Bill Ragsdale, please, the stage is yours.
Very good. Thank you very much. Great presentation today. Very, very good. Here's a tip I learned some time ago on Zoom. If you go to view in the top right corner and select side-by-side speaker, you will see the slides and you will see my lips move. And sometimes the slides are better augmented by actually seeing the speaker's face. So if you go to the top right view, side-by-side speaker, and now we will share screen. The name Enigma may be significant to some of you. I know in the computer culture, codes and cryptography and so on is fascinating. So we're going to discuss the Enigma ciphering machine. It was invented in the 1920s. It was intended for commercial use, but did not fulfill that very well. But in the 1930s, it was adopted by the German government for military communications. And for the next 15 years, it prospered, and it was actually used for about 30 years. The breaking the Enigma, the decoding the Enigma was a joint effort of Poland and England. And during World War II, they were able to decrypt a better part of the German radio communications. Here's what the Enigma machine looked like. It looked like a rather unusual typewriter. It had a keyboard. It had a plug board, which allowed the keys to be reassigned in their position. 3 rotors, which did the encoding. Some machines there were 4 rotors. We'll talk about that. And finally, a set of signal lamps, which was the output. So you would press a key, you would go through the encoding rotors, and a light would light. And here is an elegant description.
This Enigma 1 machine, manufactured in the early 1940s for the German Wehrmacht, comes in its original oak case. When I unscrew the locking bolts and lift the hinged lid, the battery compartment is visible on the right. The stator, the 3 rotors, and the reflector, lettered with a B in red, are visible. Before a message was encoded, these had to be removed and programmed according to the settings for the given day. I lift out the 3 rotors on their spindle and slide each one off. On the right side of this rotor, note the 26 brass electrical contacts and the adjustable ring, and on the left the Bakelite thumb wheel. I adjust the ring setting on one of the rotors and reassemble the 3 rotors in a new order on the spindle. Each rotor has an identifying Roman rotor number. Finally, I reinsert the rotors on the spindle and lock the entire assembly in place. Note how the rightmost rotor advances with each keystroke. After 1 full revolution, the rotor to the left will advance by 1 position, resetting the pattern of the electrical contacts. A further level of security is provided by the front plug board, or stekkerbrett. There are 26 double sockets and 13 cables, each with 2 pins. The German military generally used 10 cables. Here all 13 are attached. Finally, I close the machine lid and the front flap of the case to ensure that the cables are correctly positioned. Next, we set the power supply to external and set the rotors to the 3-letter key for the day. Let's type in the word Enigma. When the E is pressed, the bulb for J turns on and the right-hand rotor advances 1 increment. Similarly, N becomes T, I, R, G, B, M, E, and A, C. In this segment, we see how the rotor turns with each keystroke. The Wehrmacht version of the Enigma machine used numbered positions for each letter, not the letters themselves. Each number corresponds to a letter of the alphabet. A is 01, B 02, and so on. To decode, I reset the rotors to the initial position. In practice, the operator would provide a new encoded setting in the message. Note how in decipherment, J becomes E, the TN, the RI, until our original one-word plaintext, Enigma, is revealed.
Now we'll see some of the components, and in the middle we will see FORTH programs that replicate this operation. There we see 3 rotors. Here's an expanded view. At the bottom you see a left-hand view and a right-hand view of a single rotor, and it's rather complicated, multiple rings in the center and electrical contacts. On the left we see a rotor as it would be in normal use, and then on the right is the exploded view. And you notice on the extreme right, there's a set of light green wires that connect the input of each rotor to the output. Here's a typical encryption example. There are 3 sets of rotors. The electrical signal enters at the top on an A. It goes through the right rotor, it's scrambled, goes to the middle rotor, is scrambled, goes to the left rotor. Then the reflector reverses the direction of current flow through a different path through the left, middle, and right rotors. And in this case, the letter G would be output and illuminated on the lamp. Here is my worksheets on analyzing one rotor, which I had to do to debug the code and to write the code. And if you see the square F with a red around it, the red F, that is the 5th letter of the alphabet. When it enters the rotor, it's directed to position 0, and the reflector position 0 is directed to position 13. On the reverse path, position 13 is directed to position 12, and out comes the letter M. This is one rotor, and of course, there are 3 rotors involved in the machine. The encryption is reversible, mirror image. If I encode an F, I get an M. If I encode an M, I get an F. So you look at the square M and you trace the little red lines all the way down, and at the bottom it comes out in the letter F. The square box, which contains a series of numbers, is actually the rotors in different positions. And this was a method of decryption called rodding. The code breakers would build up number tables such as this that were variable as they attempt to attack the code. Here's the 4th code for one letter passing through one rotor. We see the output letter is a function of the rotor itself, the rotor position, the input letter, and then the transfer as the rotor input connects to output. The 4th code passes the signal through one level. We say rotor forward slot 1, rotor position slot 1, reverse. This sets up the path, and then the little 4th code picks the transfer values. We get a position, we get the transfer, and we get a final output. So this will go one letter in, one letter out. After one letter is encoded, the right rotor advances. So in this case, we see after we've encoded the letter A, which goes to G, on the 2nd letter, the letter A would encode through C, taking different paths through the rotors. With the basic setup of 3 rotors, there were 17,000 passes, or 17,000 patterns or alphabets. This is a wooden version of it. We will notice that the carry takes place on position 3. We go from one rotor to another. I'll recycle this so we see it again, and you can watch when position 3 comes by. We're at 23, 24, 25, 26, 1, 2, and now carry. And at that point, all the rotors advance. This is an example of the turnover from rotor to rotor. On the left are the information for rotors 1, 2, and 3. On the right-hand side is the fourth code that does this. And we'll see a diagram in just a moment that simplifies it. But we examine rotor position 1. If there's a turnover, we examine rotor position 2. If there's a turnover, we examine rotor position 3. And here is the D chart for it. As I said, we increment rotor 1. If there's a carry, we increment 2. And if there's a carry, we increment 3. This is the fourth definition for rotors. Now, since there are 2 paths through a rotor, we need to have 1/4 word for the path in the forward direction and a mirror image of it, of the rotor connections on the reverse. In this case, we have the incremental value. So if we look at the first rotor under rotor A forward, the entry 0 is a 1, so it means the output is 1 position to the right. The numbering and offsets here are very systematic, which aids in our debug. In the normal rotor in use, these connections will be random, and there are 3 different rotors, and they're all random. By end of life, there were actually 8 different rotors that were in use. This is the reflector. The reflector is actually a bit simpler because the input and output are in one single array. In this case, I just put an offset of 13. So every letter just reflects 13 letters away. This defines particular slots. It's the fourth code for defining a slot, and the parameters would be the forward rotor, the reverse rotor, its position, and its turnover location. So the operator would put in the given rotor, he turns it to a given position, and then with a little thumb tab, he sets the turnover position. The fourth definition for the rotor itself, we are defining a number of different slot types. So we use create does. So the create part has 4 cells a lot. There are 4 32-bit parameters per slot. And the does part is very simple. We just add an offset. So we've defined below that slot 1, slot 2, slot 3, the reflector, and also we have a parameters fields for the plug board and for the keyboard, which in this analysis have been omitted. Now we actually define the parameter fields. And earlier today from Ulrich, we saw a database setup. We are using that very same concept here. The 0 offset is our rotor forward. The 1 cell offset is the rotor reverse, and then the rotor position and turnover. Very fourth-like. Here's the daily setup by an Enigma operator. Operator would first select the rotor for each slot, as we saw in the video, select the turnover point for each rotor, set the rotor to initial position, and then set the plug board settings, if any. This information will be published on a monthly basis, and then the operators on the each day would have some variations they could inject. This is the initialization of the machine. This exactly mirrors what an operator would do. If you read the code down from the after start, we say rotor 1 forward goes into a slot, rotor 1 reverse is assigned to a slot, and the offset position and starting positions I've just set as 0. Normally, in real life, there would be specific values here. Slot 2 is set up, slot 3 is set up, and finally the reflector. So now we've initialized the virtual Enigma machine, and we can encrypt 1 letter. In this case, we have 1 letter in, a number which is 0 to 25, and 1 letter out, 0 to 25. Level by level, slot 3 is initialized, and then the green 1 level takes 1 letter in, 1 letter out. That's passed to slot 2, that's passed to slot 1, goes through the reflector, comes back in the reverse direction, and out it comes. In this case, we're saying letter A to G. And due to the structure of the rotors, there are 17,000 combinations. This is the setup for a test. This is a mimic of what an operator would do. Start sets up the virtual machine. Then the rotor position of slot 1 is set to 5. The turnover is set to 12. Slot 2, the position is 5, the turnover 6, and so on. And then finally, full alpha test. In this case, we'll run through the full alphabet. This is the encoding of a 26-letter message. This 26-letter message is the letters A through Z. And for debug and learning procedures, the position of each rotor is tracked from input to output. So running down to the green pointers, the input letter P on the left goes through the 7 variations and comes out as the letter I on the output. This is a little bit of the dynamic during debug. We see in the green square the example of turnover. At the beginning of the turnover, rotor 1, 2, and 3 are set to 20, 5, and 11. And when we get a 3-rotor transfer, they end up being at 21, 6, and 12. In the blue square, we see the encoding from the previous page. Position input 5, 15 is the letter P, and the output is the letter 8. And then I have the third column, which shows the 5 again, which is for checking. So this way we put a letter in, we do a letter out, and then we reverse the process and decode it to make sure we're getting the letter out. Here's some small fourth words that are helpful. One is to convert ASCII to integer. Well, that is very simple, which is just subtract the ASCII bias of the letter A. To go from the integer back to ASCII, we just add that offset back in again. My data structures are all on a byte basis. And I had a good head scratch partway through this because the numbers just weren't working right. And then I realized that when I'm doing math on bytes on a 32-bit machine, I've got to do a sign extend. So I whipped up a little sign extend that takes the 8-bit byte values to 32. And finally, bounded, all these rotors are in modulo 26 that go 0 to 25. So whenever we develop a letter combination, we limit it to that range of 0 to 25. This is the encoding and decoding. Under the red encode, the sample out 20 array start clears the workspace. Then we take sample out, sample in, and count, which develops the address of our input string and our output string. Then we just run a loop through for the proper number of times. In this case, this is set up by a 200-letter message, pardon me, a 26-letter message. And those do loops there are doing the letters till the range of the input string is exhausted. The input strings are counted strings. And since this is symmetrical, the decode is the very same. The first 2 lines take the prior output message and then generate a check message. Here's an example. I was looking for something with historical significance, and originally the Morse code message that was sent from Washington to Baltimore for the initial test was, "What hath God wrought?" Well, that's a little too short. So I went to telephone history, and this is the first message sent by telephone from Alexander Graham Bell to his assistant Watson, room to room. And this is directly from Alexander Graham Bell's notebook. "Mr. Watson, come here. I want to see you." This is how the plain text would come in. For encryption, the words are separated by the letter X. Notice that the Enigma has 25 letters, no spaces, no numbers, no punctuation. So everything had to be spelled out in 26 letters. So an X between each word, and at the very end, the end of message is a Y, and then there are 3 X's added at the end because this is sent in 5-letter code groups. When it's encoded, you see the random scramble. As transmitted, there are the 5-letter code groups. And then when decrypted, it comes back to, again, "Mr. Watson, come here. I want to see you." Here's the performance of my fourth implementation with that very same message. It took 62 microseconds to encode and essentially at the same time, 62 microseconds to decode. I was quite impressed at the speed of that. There is no intent here to optimize. And if this was real life in decrypting, you would write several of those code words in code, and it probably would slide down to maybe 25, 30 microseconds. Here's an actual log sheet for World War II. There was an extensive, huge effort in intercepting of messages. There were some 70 intercept sites that the Allies ran around World War II, including into India and to Egypt, into the Caribbean, into the Mediterranean, and into Spain. The message in the middle, you can see the 5-letter code groups. There's a lot of notations on here on the frequencies, the time of day, and a lot of analysis was done by the code breakers in Bletchley Park. This was their raw input. So here's an analysis of some of the components of an attack. In my case, to decrypt all the basic rotor settings, there were 1,054,000 combinations. And in my implementation, this would take 1,034 seconds. However, the naval Enigma in the middle of the war went to 4 rotors, and using the plug board, it became 10 to the 11th combinations. So if one is doing a brute force attack using my system, which is a 2 gigahertz clock cycle, it would still take 2.8 years to exhaustively try all combinations. Bletchley Park methods were 20 times slower. They used an electromechanical system called a bomb. They could do 52 tests per second. And they actually worked by accelerated methods where they could run through the entire cycle in 22 minutes. So how did they end up breaking the codes? Well, they had math analysis. They had to have lots of messages. They had the electromechanical aids, which we'll see in a moment. And the operator errors gave them help and clues along the way, ultimately to a number of what they call pinches, which were seized German U-boat code information. And I put it all together and ultimately were able to attack and master 70 different cyber systems. Initially, the Bletchley Park group used manual methods of sliding rods. The rods had inscribed in them the patterns of the rotors, and they could line them up, get clues from the usage. And in this case, the rods would take them anywhere from a couple of hours to a couple of days. They were not quick. They used tricks. A lot of times they were ineffective. From about end of 1942 on, they developed under Alan Turing's guidance the machines called bombs. As I mentioned earlier, when the Enigma went to 4 slots and 8 rotors, for 7 months, they were unable to read the German naval Enigma ciphers, and this was during the Battle of the Atlantic, which was a critical time, and the code breaking blacked out. The development then of the electromechanical bombs led by Turing would deliver in decryption in 1 hour to 60 hours if it worked. It didn't work all the time, but it was going to work. They could generally do the preliminary work in 10, 20, 30, 40 hours. And then after that, then they could break a code in roughly an hour. So as we see the scrambling that they were trying to decode went anywhere from 1 million combinations to hundreds of millions. As a comment, the early work was done in Poland before World War II, but when the machines were advanced, it exceeded what the Poles were able to do. So they turned over their material to the British, who formed Bletchley Park and took over from there. Bletchley used hand methods, alphabet charts, the rods, group theory. They brought in from Cambridge and university mathematicians, and a lot of people who were good at chess and good at crossword puzzles. This material would not have been possible, or the codes would not have been possible to break, except they were able to capture German documents, and there were systematic errors or random errors made by code clerks. For example, the code clerks sometimes would use as the key their girlfriend's name. Sometimes they would use German swear words, and sometimes the British were able to catch these patterns. Later on, there were the electromechanical machines called bombs, and a machine that we will not discuss, which is called Colossus, which was a vacuum tube machine, but that's a whole different story. Here's a picture of what one of the bombs looked like. They weighed a couple thousand pounds. They were about 6 feet tall, about 14 feet long. And those cylinders in there replicate, each one replicates an Enigma machine. They would synchronize them, run. They would run for minutes, clickety, clickety, click, when the machine would lock. The operator would write down potential settings, start the machine again. Those potential settings were passed over to human operators who would test them. Here is a reconstructed bomb. Somewhere in about 1992, the British Computer Society, BCS, took on as a project reconstructing a bomb, and they built this machine. It was done by volunteer labor with, I understand, volunteer money, maybe contributions. But at that time, Bletchley Park was not a museum, and they showed no interest. In the late 1990s, Bletchley Park turned into a museum, and then they got the final operating bomb, brought it there, and it's now on display. Here's the programming of it. You can see the rotors on the left and then a plug board on the right. They would enter in a test message because they would run the bomb, searching, trying to find fragments of messages. Typically, the first three letters might be for an Italian message, PER, which means per. So they would look for PERX. Sometimes the introduction was personale, which means direct, and so that would be PERS. So the bomb would be set up searching for these patterns, would run through, click through the patterns. If that first crib didn't work, they would try another one, another one, another one. So to summarize, this became a huge effort producing these bombs. This code breaking, as we'll see, was a gigantic effort. The peak production was 2 bombs a week. So what we just saw a moment ago, they had a production line turning out 2 of those a week. By the end of the war, there were 155 of the 3-letter bombs had been made and 180 of the 4-rotor. And these were made in National Cash Register's Dayton, Ohio factory. And by my research on it, it appears that 100% of that factory capacity was given over to producing bombs. They stopped making cash registers and they started making decryption machines. The intercept stations were radio stations scattered around. As I mentioned, there were 40 different intercept stations. Each intercept station would have 20 to 30 operators and a huge antenna farm. It's estimated they did well over 500,000 intercepts. And at the 1945 peak, I saw in a reference, they were breaking 18,000 messages a day. I think that's a little ambitious, but that's what the reference said, 18,000 messages a day. Bletchley Park did have a staff of 10,000 people. As I say, this was no small effort. Some of them were in things like cafeteria and transportation and maintenance, but the bulk of the staff were people intently working on these 30 or 40 different encryption systems. The output was known as Ultra, and Churchill was fascinated by this, and he arranged that it had full support, so he was able to read secure messages all through World War II. The Enigma went through 20 different production variations, from the commercial to the wartime to the post-war versions. And the British codebreakers had to keep up with these production variations. Interestingly, Britain continued to sell Enigma machines to other countries around the world, into the 1960s, and they maintained as a secret that they kept this code breaking ability. So England was selling encryption machines to other countries, knowing that they had tucked away the bomb machines that were breaking those codes. This whole process was a total secret until 1974. And when you read the books on this, you see the intent on security was intense, because they knew that if Germany realized they were breaking the codes, the system would change and it would go dark. And finally, there were many software implementations, such as the one I did, which exist today for the Enigma and for the bombs. As a final aside, here we see a recovery that was done in February of this year. There were divers who were removing abandoned fishing nets from fish sanctuaries. And one of them said, I think I see a typewriter over there. So he retrieved what he pulled up, and sure enough, it's an Enigma machine. And this has now been added to the museum stock. There's my references on this. If you go to GitHub under Bill Ragsdale, you'll see Forth projects, and you'll see the Enigma machine. We'll stop the share, and we come back, and if we have any very brief questions, otherwise we're probably long on the program, so we ought to keep forging ahead. Thanks for your kind attention.
Do you think the people in Dayton, Ohio at National Cash Register had any idea what they were building when they were building the bomb machines?
Baseline answer is they didn't have a clue. I'm sure bright people might have figured it out here and there, but even within Bletchley Park, they petitioned need to know. And for example, the British Post Office designed a machine called Colossus that was vacuum tube machine, and only about 3 or 4 people there even knew what the machine did. Everybody else just followed the diagrams and put it together. So there's any number of books on this, roughly 15 or 18, 20 different books covering World War II. So look them up. The stories are fascinating. One is called Breaking the Enigma by Kahn, and that went very heavily on what the tools were that were used to break the codes, not how they were doing it, but what resources they had. Anyway, thank you very much.
Mm-hmm. Great. Yeah, thank you very much. So as I can only encourage, if you had the chance to go to Bletchley Park and visit the computer museum there, that's really worth a trip. So if this is possible for you.
As an aside, there were something in the range of 10,000 Enigma machines built over that 20, 30-year period. And I understand that about 450 are known to exist today. So they pop up on auction occasionally, and they typically go for about $200,000. And there's about, as I said, 450 a day. I went to a computer conference one year, and they had a machine there that we could put hands on and we could use it.
Yeah, that's great. Right. So yeah, Bill, thank you very much for the interesting talk. And so we're in the salutation part and about to announce what we do next month.
We don't have anybody in the salutation for today, Ulrich. I was hoping to see Rick Carlino, who helps our group sharing what we do on Twitter. He's a great friend, and I also want to thank everybody, because we had a lot of people, friends of our group, sharing our Zoom meetings in different Facebook groups. Bernd was sharing in the analog group, and other people in different groups. John shared also in another group, and etc. So we have a lot of support for these meetings.
That's great. So, but Rick didn't make it here. So Yeah, no one today, but there is an announcement for the theme that we want to have at the next meeting. Is that right? At least that's what I read in the schedule, announcing next meeting theme. So do we, so last time robotics, this time, I don't know.
No, it's a general announce, calling our friends, our new members of the group. But I don't know who wants to say hello. Who is new in this meeting?
No. You don't need to be shy. You can just open the microphone and the camera if you want to just say hello.
Yeah.
Yes, hello. This is Jonas here. I was invited by Peter.
Hello.
Hi. Yeah. Sitting
Super,
in Bangkok.
Jonas. Wonderful to see you.
Yes.
Where are you from?
Oh, I'm Swedish originally, but I'm in Bangkok as of a year and 10 years in Asia. So I was in Hong Kong previously. Now there's no going anywhere, you know.
Wonderful. So, yeah. Very nice to see you. Thank you for participating. And in future, if you have any team you want to discuss with us and show the group, Jonas is also a FORTH programmer, no? What are you doing with FORTH?
Oh, I'm playing with 6502. So I wrote a simulator for 6502, and I'm intending to write a FORTH interpreter for it, and so it's kind of simulated in JavaScript, which is all ridiculous, but it's what I can do and the tools I have. So I wrote an assembler in JavaScript, so it's kind of a macro assembler written in JavaScript, so you can do everything, and I'm using it to generate code. So
oh, very good, very nice.
I'm working on various variants. I just posted something in a comment about a headless FORTH where you basically you get the 6502 to run source code of FORTH, a textual source code of FORTH, where you say 1+ and actually the way it works is that you just jump to the space, because the space on a 6502 is a hex code 20, which is a jump subroutine. So basically, you just put all the subroutines on 2-letter combinations in memory, such that you can dispatch on this. So you don't need an interpreter, but of course, you waste a little bit of memory.
Cool,
just
very good.
Playing fun things.
Nice.
All right, thank you.
Okay, who is Martin? Martin is bitter. From where are you, Martin? Are you going to leave the meeting, or what is happening there?
Yes,
Martin.
I will have dinner with my family. I'm a retired teacher for disabled children, and the last 20 years I was working on something we called inclusion in Germany, that is educate mentally retarded and disabled children together with so-called normal children. And I came to FORTH 1984 or 5 because I wanted to write programs for my pupil, and there weren't any programs in the market for this group of pupils. And now I call myself an eternally beginner. And so I'm here to learn about something about the ESP. And I hope the lesson after the coffee break will be interesting.
Of course, yes. We are going now to we say hello to you and to your family. Go to a dinner or for a break. We make 15 minutes, okay, Ulrich?
I think so. Yeah, 15 minutes.
Okay, then I will hurry up.
Yeah. We will record this anyway, so that's not not an issue. If you miss the first few minutes, that's not a problem. So, but we can announce our next meeting, which is in July, on the 10th of July, always the second Saturday each month. And the 10th of July is this Saturday in July. Yeah, right. So you can scribble it in your calendar already, or maybe you have a reoccurring appointment there anyway. So yeah, enjoy your coffee, and we'll see us in 15 minutes.
In 15 minutes, bye-bye.
A quarter past, whatever hour is at your place.
Yeah, Peter, had a problem. You know, this morning, yeah, I was spending about half hour trying to log in, but unsuccessfully, until Bill gave me the secret code that finally get into the meeting. What happened?
You have the Facebook. You are in Facebook, so you see our invitation. It's only click. There is a button, a blue button, join, and the meeting starts.
Oh, okay. Well, I was typing in the zoom.eforth2020.org, but never could get in.
Okay, if you are in Chrome, in Google Chrome, you only type this, but not in a Zoom. You must be on the browser. You type Zoom FORTH2020.org, and it will start automatically.
Wow. Thank you. I was kind of frustrated not be able to get in.
We can practice this anytime, Dr. Ting. There is no problem. We can practice this.
Thank you. Yeah.
With other friends also, because I hear some of you have problems, and it should be very easy now with this link.
Okay, thank you.
Thank you to you, Dr. Ting. It's a pleasure.
How are you doing, Dr. Ting?
Oh, pretty good, pretty good. Thank you. Yeah, good to see you.
Here, I wonder.
Yeah.
That thread with your Java. It's haven't done a ton of late, but the one thing I have an using Forth, but
Pablo? Pablo, I have a question for you. Can you hear me?
Yes.
Okay. Yeah, your fourth implementation on the ESP32 was really interesting. Apparently, you were able to get down to the CPU. I just couldn't find any good reference on the how to access the CPU. How did you do it?
The program is only in C, no in assembly. You reference to how program the virtual the interpreter.
Yeah, you didn't get down to the CPU level. You just write everything in C.
Yes.
Okay.
Dr. Ting, if you are interested in diving down to the next level below, I have found the documentation for the instruction set. It's here, I'll paste it in the chat. I can manage to cut and paste.
Yeah, it looks like it's a strange 24-bit machine.
Yeah, it's got a, I mean, it's 32-bit like registers, but it's the instructions are mostly a mixture of 16-bit and 24-bit, depending. There's sort of it's a little bit like there's sort of a little bit like ARM. There's the long instructions and then
Your audio is breaking up.
Let me try a different setting here.
Dr. Ting, you asked about the implementation of the My Virtual Machine.
Yeah, right. Yeah, it looks good.
It's very minimal, yes. Really, it's not by code. It's the word codes, 32-bit every token, and the lower 8-bit are the reference to the instruction, and the upper is filled with the address or the literal, and for make in one access memory to do every byte token.
Mm-hmm. Yeah, the bytecode was very interesting. Yeah.
I have in Spanish a conversation with Cecil Bayona in YouTube about the internals. It's difficult to me express in English because I think in Spanish, but I try to learn.
Yes, I did the same thing with Chinese.
Okay, yes, the same.
The same.
One idea. One idea would be if you write it down in Spanish, then we can use DeepL to translate this, and this works quite well right now. So you just write your thoughts in Spanish, and we use the DeepL translation service.
Yes,
to translate it to German, for example, or
we use an Enigma machine, Pablo, and we translate in
or that.
For me, it's better writing, not talking. Nothing. Well, if you like very a specific explication in the virtual machine, tell me and I try to make a documentation.
Okay. Yeah. I really appreciate it. Yeah.
Okay.
I had a few questions on it. One, which I know Dr. Ting will also have an answer to this, but is why use bytecode?
Why?
Yes, why use bytecode for the interpreter instead of, say, subroutine or direct threaded or native code?
No, first is you can access to assembly code in Android IDE. Not have access to extend that, no? Extend the CPU, algo así. And we need this layer of virtuality, and then make a virtual CPU that execute these bytecodes, and then you have access to compile in without access to assembly. This is why.
I see. So you don't have to have an assembler. You can always just compile to bytecode instead. And have you looked at what the bytecode looks like once you've compiled R3? Do you ever look at the bytecode itself to see that it's how you would expect?
Again, I don't understand.
So when you write R3, it compiles to bytecode, right?
Yes.
Have you ever looked at the bytecode produced by the compiler?
I don't understand what you asking. Is when I compile to bytecode, yes?
Yes, yeah.
This bytecode?
Yeah. Do you look at it? Do you read it yourself?
Yes. In the SP32, if you type list, you see the bytecode colored. Okay.
I see.
And the first approach is working all in the token space, like Spectrum or yes, like Spectrum or all basic, GW basic, and then. But it's much better working with source code, and for me, programming view all the source code like text, and then compile and execute later.
I see. Okay. So since it uses bytecode, could somebody implement the CPU, say, for example, on an FPGA and run the bytecode directly?
In a FPGA, it's better make a for machine directly. No bytecode, no have sense. The bytecode are the assembly language of the virtual CPU. If you can design these instructions, the better for me is make a machine for a fork with jump, with call, with lead, and make a layer of interpreter with translate the classic fork or whatever in this machine fork. It's like word color fork. Color fork is a very good source of inspiration in how work fork and in assembly level.
Yeah, I think bytecode is very interesting. It's a very good media between machine code and C code. And the other thing is that of course the best or the most important bytecode is Java bytecode. If we can make a bytecode machine executing Java bytecode, that will be big achievement. But the Java bytecode is quite involved because it specifies the integers are all 32 bits, but it also includes the long 62-bit long integers and 32-bit floating point and 64-bit floating point. So doing a truthful, faithful implementation of Java bytecode, it is quite difficult.
Yes.
Yeah, I'm trying to do the cut down version of the Java real machine with only integer part, only 32-bit integers. I think it is doable. And I think it would run on a FPGA.
All right. I think coffee break is over. Maybe Martin is.
Before you get started, this is Christian. May I ask a question to Pablo?
Yeah, sure. Go ahead.
Okay, Pablo.
Yes.
I'd like to know if I understood well your R3 type of FORTH. I'm a beginner with FORTH, and I'm using mostly ESP32 FORTH. The question I had when I watched your presentation was, what is the main difference between R3 and ESP32 FORTH implementation that makes your R3 so much more flexible, or fast at least?
No, fast not, because the ESP32 is more small. Yeah, and the language is the same. I remove the R stack words, but it's an experiment. But and the other difference is the not have a frame buffer, graphic frame buffer for memory problem with the microcontroller. But the language is the same. The editor made in R3 is almost a copy of the editor made for the PC. The language is very tiny, and because this is very easy to transport to other machines.
Excuse me, are you using the ESP32, the same one we're using?
Again?
Well, but the problem is the following. Sorry to interrupt you, but we have a schedule, guys. This is not time of Pablo. This is the time. Sorry, but this is the time of Brad Nelson.
Okay, thanks,
Brad.
So we can't hear you. Why is this?
Is that better?
Brad can follow.
Yep, that's better.
Okay. The main thing today actually is that Peter has an excellent website that I think folks should take a look at. Peter, before you, I think I would love for you to present that. I do have a little bit I can show off with the ESP cam, and then perhaps go from there to the website, or you want to start with the website?
Okay.
Go for it with the website. Show the website. It's good.
This is a short 5 minutes I will take, or 3 minutes. This is important because everybody who is working now in the ESP32 community we created on FORTH2020 group, there is so much work, guys. It's incredible. Look at this. Look at this. It's fantastic. All what we are doing here. This will be promoted probably in some magazines. I was talking with some guys This is a new website. I have 4 pages of information. Look all the work people is doing around the world with ESP32 force. This is fantastic. And it continues. I will put this site now. This is all from Christian. Look, Christian here. 1, 2, 3, 4. I think Christian has more than 4. This is Jason here from Malaysia. This is Tony Leff from Australia doing the LCD. This is Dimitri Peinado from United Kingdom. This is Peter Ford from Brazil, calculator. And then we have more people. This is Jan Lagervard from Denmark. And we have also a new friend is from, I don't know which country. A lot of people helping us with documentation. So this project is growing, you can't imagine. And what are we doing? Facebook is very difficult to read because Facebook is done for the day. So you put information and then 1 month later, you can't find it. So I started this website and probably you can follow this. Let me put the link on the chat. But this is all the work. We are so happy from the work. We are enjoying the work of Dr. King and Brad. Brad is doing fantastic here. All what we ask, he creates and resolves for us is in a minute. Is fantastic what he programs. And now he's going to do an ESP32 cam. So I bought these days a cam here to start following what he is inventing. And another thing here I will share with you, my camera. We are doing the libraries mostly with Atle. Atle is also helping very much. You see I got here a magnetometer. This is the compass. This is the gyroscope here. OLED, we already did OLED. Here's the ESP32. And this is the laser sensor, this one. So for all these devices and many more, we are creating the libraries. So ESP32 force is growing and growing, and also the famous Ford Mobile. No, we are having here the Ford Mobile. This is already running autonomous. So we are expecting the presentation of Don for the Triune OS, which is so interesting. And for me, I am finished here. I put the link in the group and I follow with Brad Nelson.
All right. So yeah, slowly in the background, I've been putting in a little bit more support for ESP CAM. ESP CAM, for those of you unfamiliar with it, is an ESP32 based variant. It has a similar CPU to the ones on regular ESP32, but it also has some additional PSRAM, and it has a connector for a camera, and also very conveniently an SD card, and it's built around the idea of being able to do things with the camera. One challenge with this board to be aware of is you'll need an FTDI connector, because it doesn't actually come with a serial connector, and so you'll need to lay it out on a breadboard such that you can connect to this bridge and then talk to it over serial port. You'll also want to wire up. One other challenge is that by default, it will tend to not want to come up in a mode where just the pins can program it. You'll need to wire up a button or something so that you can power it on in a state where it's willing to be programmed. So all of these make it a little more challenging to hook up. But once you have the serial bridge in place, you can sort of boot up with the button depressed, and then have it in a state where it's ready to program. Let me show a few things with that. I'll present my screen. Let's see if let me go ahead and in the ESP32, so loading ESP32 forth is relatively similar on the device, but there are certain things to watch out for. Typically, you'll want to choose the AI Thinker board, and you'll want to be sure that you, so it is the default on this board, but you'll want to make sure that that you sort of stay with those defaults. And then the pattern is sort of, you'll need to attach that pin to put it into a mode where it's programmable, do the programming as usual, and then after a reboot, it will come up, and then things are sort of similar. Let me, oops, it tends to want to sort of reset the serial connection, which is a little bit annoying compared to some of the others. That may just be the FTDI board that I have. And then you get the system. One recent change I've made is that I've been working towards changing the way the web server works. And one of my motivations for this is that the web server library that we had wrapped up before I've discovered it to be a little bit unreliable, and it also is not going to be very well suited for things like if you wanted to do streaming video, which is where I want to be able to eventually stream video over to the device. So I'm incrementally working towards that. A new thing that is loaded in the image by default is there's now a so anyways, now I have not taken out the old web server yet. Oops, it's in the POSIX directory. But oops, that's not the right one. But there's now this HTTPD interface to set things up. And if you look at the source code for the web interface, it now relies on the HTTPD interface instead of using the web server binding. So we're sort of gradually weaning ourselves off of using C libraries, especially I've been focusing mainly on the C libraries that are actually not giving us much value. The web server library is fairly complex and doesn't actually do very much. There's now a camera server that is so far very simple. It provides two paths in the slash directory. There's a small JavaScript page that will just reload the images, and then there's a single path to capture one image from the camera. Let me go through a demo of how that works. So if you so I've got so you'll need to set up your Wi-Fi beforehand, and the usual you can do sort of your network and your password and such, and then do login instead of web UI, and that will activate the Wi-Fi. I've got that stored in a block, so I can load it without showing everyone my password. So now I'm up on the network at this port, and in the camera server vocabulary, you can start a server, and I'm going to start it on port 80. And so now at this port, the camera server is running. Let me go bring up a browser tab. And if I go to that port and load a single image, then I get a single image. Let me hold up the device so it's actually pointed at my face. And oops, I'm upside down. As you can see, the camera. And smile once more, get a better photo. One general issue with the web server is that it's still similar to the out-of-the-box web server, it's a little bit unhappy about servicing multiple requests at a time. I eventually intend to make it work better with tasks so that you could service multiple requests at once. But at the moment, it only handles one outstanding request at a time. So while it's grabbing a frame, it's not able to do anything else. Another wrinkle with the camera, for folks that are interested in the specifics of the camera API, all of that's, a lot of this is documented on the site, but the camera interface has a very small set of words. You basically initialize the camera and you need to pass a camera config. There's only a few reasonable defaults for the device because it only has a limited set of formats that it can do efficiently. And so if you initialize it with this config, so you pass in the config, you can then call camera frame buffer get, and you'll grab a single frame, and then you can process that frame. The frames come out in JPEG, and so there is library code that can decode that, but I haven't figured out. I don't currently have any plans to do anything on device, but there are some fast libraries for decoding it on device, and the device does have some support for doing that relatively efficiently. That's actually all I have with that. If folks experiment with ESP32, and have questions, please reach out to me, and I'll try to be timely in my responses. Let me stop sharing, and any questions?
There was somebody from Germany. Is he back? Who is his name? I don't know.
Yes, I'm back.
Do you have any questions?
Not in the moment. I will visit the website and look at the recorded video, and maybe then will come some questions.
Okay.
But not in the moment.
Atle, how about you? You are developing a lot with this ESP32.
Well, I'm back at this stage again, so but it's running. No, the questions that I had was relating to the ESP8266. And I'm not really sure if that's up Brad's alley or Dr. Ting, but it's just that I want to be able to, if it's not possible in any other way, I would like to be able to just dynamically link in some library code. If it's not possible to do it in another way. That's been what's going around.
I think it's possible. I think the challenge is the tools that we're working through, right? If to the extent that we use the Arduino tools are sort of everything is sealed and it's not terribly easy to do things. With the raw ESP tool chain, it's likely possible to build a relocatable library and bring it into memory and do interesting things. The challenge, I think, working with a sort of wider group is that what I found, at least so far with ESP tool chain, is that setting it up, whichever version you need to sort of be the latest one, they like to make changes to it underneath that are incompatible. It's very hard to get people on the same version. Oftentimes the latest version that's readily working on Windows may not match the one that's working on Linux. And so depending on what platform folks are on, it can be challenging. That said, it is sort of the Arduino tools are actually implemented on top of that tool chain. They actually are behind the scenes downloading a copy of that, and they just have pinned a particular version that they're pulling down. So unsure. Are you trying, the hope is to be able to sort of build the libraries once and then not have to fiddle with them? Is that what you're going for?
No, well, what I really want to do is put forth on my old, because I've built a couple of rovers and I'm running them with C code, and then I would like to change to forth. But they are using the Wemos Mega. board that has a Mega and an ESP8266 on the same board. I'm using those, and then I'm using this 8266 as the strategy chip, the captain of the boat, and then the other one is the machinist with all the I/O and all this stuff. And I would like to put forth on all that just for my own pleasure, not for anything else.
Certainly the Mega is a great choice for that kind of thing because it has so many I/O pins and it makes a lot of sense. I haven't originally, when I put together what's the current iteration of ESP32 Forth, I had some imagined making it flexible to support ESP8266, but I haven't tried in a while. I have a few floating around. If I may try to dust that off. I would imagine it might work, but it might also be very tight. It's a little bit more of a wasteful Forth than it might be on a tighter chip. Dr. Ting's ESP8266 Forth is probably a little tighter, but I think it also depends on what's the interface between your Mega and the ESP8266. Is it?
Have you looked at that board?
I have used that board in the past.
Yeah, you sit and flip dip switches all the time, so you so that they're almost worn out now.
Actually, the problem I see is when we compile this force, you have seen the ESP32 force is 1 megabyte.
Yeah.
So the ESP8266 has no space for a force.
Yeah, I would imagine if we swapped out a lot of that size, Peter, is libraries that we're pulling, right? Because we're pulling in all the different things. The trouble is, it depends on which libraries you'd actually need for your application. Like if you need, the biggest ones are things related to Bluetooth, for example. That one uses a lot of space.
Yeah, well, I wouldn't need it. I would need Wi-Fi. Then I would need the PCM, this card. Then I would need the compass for steering. Well,
you have no more space. You're out of space.
Yeah.
The problem, Atle, this costs only $3 in the moment. This chip, this ESP82, this ESP32 costs $3. So I don't see any necessity to go back to the other one, except in your case. I know, I understand your case, no?
Yeah, well, there is this thing about power consumption still, but well, with these batteries, they don't empty for. They can run for hours. So yeah, you're absolutely right. It was just as a fun exercise for myself.
One thing I wanted to mention to the group that I've been noticing lately, I was going online the other day to shop for more ESP32 boards, and I'm starting to see far more of the ESP32S2 in the market. And this one is interesting. This has been around for a little while, but the issue is that right now it's not supported in the Arduino toolchain. And so if you go down to the direct toolchain, you can support these, but be cautious if you're looking for a board that is compatible. These don't work yet. My understanding is that the Arduino folks are shooting for support for this device sometime around the end of the year. It is sort of just like the ESP32 is a superset of the 8266. This one is yet a superset of the ESP32. I think it's got maybe twice the flash and more RAM and things of that sort. It is a different CPU though, and so it's likely that within Arduino it'll be sort of yet another sort of split. But I am starting to see these more often. I actually almost accidentally bought one, so I actually probably will buy one and play around with it with the raw toolchain at some point if I get a moment. But I suspect that this will introduce another layer of confusion because you'll now have these boards on the market and they're sort of not mutually compatible. So, yeah.
Oh, one more thing with your ESP cam. Are you using this facial recognition part? Have you tried it?
I have not tried it yet. There's a bunch of libraries that that folks have ported, and I have tried some of the demos, you know, that folks have produced. I haven't actually. Maybe I have tried the facial recognition one. It's fairly low frame rate. Like it was only, I think, able to do a face detection at about like 8 frames a second, if I'm remembering correctly. The issue is that the camera is actually its own little separate, it's the OLV something or other, and it sends the data across as JPEG data. The CPU has to decode it to get out the raw pixels because it's coming over as JPEG data, and then it doesn't have a lot of time to then go and do some basic image recognition. So it's certainly possible, like there's enough time to decode, I think 30 frames per second and get the raw pixels, but after you've got them, you don't have a lot of compute left to do a huge amount. You can do some, it might be, you know, yeah. So yeah, it's definitely possible. I suspect that another thing we'll run into is that if we're doing more things with the video footage, all of the slowness of the interpretation techniques we're using with Forth are going to be an issue if we want to do any kind of image processing, which is another reason why I'm tinkering. In the background, I've been tinkering on an Extenza assembler, because I suspect we'll need some code words for if we want to do anything terribly interesting with image data coming over from the device.
Well, I did some communication between the ESP8266 and a mobile phone. What I had the ESP8266 just spew out UDP packets, not thinking about whether or not they were received or what, and then have the mobile phone process this with more intelligence. It was telemetry data from the sensors and stuff like this, and it just spewed out UDP packages all the time. I was thinking, would that be possible with say JPEG frames?
Yeah, I mean, and certainly, like for one of the ways that we could solve these problems, if we're just sort of wanting to do things, and it's okay to have the work being done, say in the browser, you can definitely just send over the JPEG data and then deal with it somewhere else. The problem is then you're tethered to a device and you have to sort of care about that. So it depends on the application, right? If you just want to stream video or you don't care about doing the processing of that video somewhere else, then it would be fine. If you want the device to be sort of standalone, that would be where you would have an issue.
Yeah, the dream, of course, is to have the FORTH-mobile know a little bit about its environment so that it can crawl after the cat, for example, or something like that. Knows it's a cat, it knows it's a person.
My guess is that a clever person could probably do more than the 8 frames per second for the face recognition. They're taking a very vanilla off-the-shelf library and just applying it, and so something a little more custom, sort of purpose-built might be able to be more efficient. But we'll definitely need to get down to the metal if we want to have enough compute to be able to do anything interesting on device, I think.
Yeah.
Did I hear that correctly, that there is still no assembler available for the ESP32, at least not the fourth?
I'm working on one. It's a work in progress right now. It's not done yet.
Okay.
Hope you have it soon.
Are you well? I have some experience with writing assemblers. A lot of them, for including the Pentium, including the DEC Alpha, including 6809. So maybe I could be of some help.
Yeah, maybe what I need to do, I've been so far sort of laying out the structure for the thing. I'll try to be sort of post early versions of it, and maybe perhaps we can collaborate. It's been something on and off. One of the things I wanted to do with it that maybe is misguided, and is why it's probably taken longer than it should, is I was trying to both simultaneously do an assembler but also a disassembler at the same time, and that makes it more tricky. Like the actual instruction set, there's only a sort of a core part of it. It's a nice RISC instruction set, And so there's actually not that many encodings that are, most of the interesting instructions that you would want for a code word in Forth, there's a small handful of styles to them. And so if I was just focusing on the bare minimum, I probably would be doing better, and that maybe that's the pivot I need to make. But there's a lot of instructions that are sort of packed in there for things that we
maybe then my type of design for assembler is interesting, because once the assembler is ready, the disassembler is free. And the reason is I use objects for all parts of the assembler separately for the opcode and for the operands and for modifiers like indirect. And then a surprise, you can put them in in any order first. And secondly, you can use the objects to reconstruct the original in a code sequence. And and that's called the post-it fix-up principle. And I have an assembler of that type on the website or on GitHub, and it's called See As This.
Could you paste the link to it in the chat? I would be fascinated to take a look.
Yeah, okay, I'll do that.
Yeah, it's a one other wrinkle, of course, that I've been thinking about with all of this is debating with myself a little bit about the floating point on the device. It has a rather substantial floating point and to some extent SIMD capability. And so far, that's something that we haven't exposed at the sea level. And I think that on the one hand, that will make that code more complex. But if we rely only on code words to access that stuff, it may be more of a hassle. So I don't know. I've been debating. It's an unusual situation because unfortunately, for a device that has floating point, while in general, lots of things you can do without floating point, we're sort of missing out on half of the chip's raw hardware capability by doing that. So.
Yeah. Okay.
Yeah, that brought up the point, because I've been thinking about that too, trying to use floating point on it. And I guess the advantage Dr. Ting had with his JavaScript is JavaScript, I guess, duck types. And, if it looks like a floating point number, it processes it like a floating point number. And you're working in C, and I'm trying to, there is no easy way to do that in C, is there?
No, I mean, we could certainly add conventionally Forths will have a separate set of words prefixed with like an F for floating point and have a separate float stack. But I think that the thing is, particularly for the kinds of applications that we would probably care about using floating point for, maybe processing images, for example, the challenge is that a sort of float stack is likely to be relatively inefficient on this architecture. And so I suspect that it might almost be simpler, to just have a code word that temporarily drops into using floats for special purposes. But on the other hand, it's inconvenient to have a data type that you don't have exposed at the level of Forth that you're using, say, in code words. So I'm of two minds on that question. And
John, a question: what are you doing with ESP32 Forth? Have you installed? Have you tested?
I have one device. I'm able to blink an LED with it. I mean, I'm a real newcomer to Forth, and some of the code that I saw today was, I mean, the Enigma code was beautiful. And
I propose something we can do anytime with everybody who wants, Atle or Christian or who wants to participate with us, a workshop about ESP32, and we show this is all beginner stuff. There is not, here we don't have any specialist except Brad and Dr. Ting, of course, but the rest of us, we are talking as beginners.
Yeah, no, and I appreciate that, and it's a great group, and I mean I was blown away with the Enigma presentation, and we have a very diverse group of computer people in this group.
No shy, no shy. Simply ask and raise your hand and simply participate with us. We need more participants. Okay, if you, Brad, if you don't have anything else, we need to continue with Don, with the Triune. Don, are you there?
Yeah, I'm here. All right, I'm ready. Let's see.
Okay.
All right, you can see my whole screen. Okay.
Yes.
Yes.
Okay. Let me stop sharing for a minute. So there's a couple devices I ran across. This is a LiDAR that only costs about $200, and Garwin is selling them. Let me put it's something as roboticists we need to use. Let me put it in the chat here. Let's see. LiDAR is quite an important sensor for long range. And if you don't know what LiDAR is, it's basically you can scan a very long distances and get a very fine beam. And if you mount it on a motor, then you could actually get very precise, like look at a tree, 20, 30 feet away, something like that. This is another device. So this is a speech recognition board for $50. And it's this company. I'm going to put that link in there. So what this does is it takes a voice and it creates, text. So it's a voice to text machine, and you plug it into your serial port, and now you can talk to your robot. So that one is this company. All right, so now I'll start my presentation. All right. Show you Whiskers first. So this is Whiskers, all right? This is it's got a an 8-bit microprocessor, right? And it's got this is a 68 8C11. It was sold back in the 90s. It's a 8-bit microprocessor that the whole fourth triune system compiles down to 32K. And then there's a battery backed up RAM chip. We didn't have non-volatile RAM, or so this is just simple SRAM. But when you turn the robot off, it keeps the it keeps your words, whatever words that you added to the system is compiled into this. Whiskers has, obviously, where's his name comes from. He's got 2 whiskers. Somebody has their mic open. He's got, these are his eyes. These are LEDs, and there's actually a photo detector in front of his eyes. You depress a whisker, he reacts to it. You can also grab a wheel, and that's a sensor of last resort. Okay, he just got mad. Whiskers doesn't just run programs. I'm going to grab his wheel. So he actually sensed grabbing the wheel and he reacted to it. So the idea between Whiskers is you have a 3-level artificial intelligence level program called the Triune OS. I'm going to show you him doing some collision avoidance here in a second, and then we'll go into the Triune OS. You're going to have to tell me, because I can't see the screen, you can see everything. So you can see Whiskers okay?
Yes, we see him fine.
Okay. So we're going to follow Whiskers around here. Now, he didn't see the shoes, but he sensed it with his motors, you know, the motor current. He's just using instincts and behaviors. Now, he just got mad. He got pissed off. And now he's going to try, he takes a random position to try to get his way out. So now he's going to go down. He's going to try his thread his way through. There's a book that everybody should own. He got pissed off again. So then he sensed that. The optical sensors aren't seeing the black very well. So the interesting thing about getting mad, it actually works well with collision avoidance. Okay, so he's singing a song. So he's singing a song in the foreground at the goal level. Now, if I press a whisker, you notice his wheels are going in opposite directions, and he's still singing the song, which means he's doing this in the background. The instinct level is actually created in an ISR, interrupt service routine. So now I'm going to activate one whisker and then the other one. Now that's a behavior. So that's a double whisker hit behavior. It takes control from the goal level. And so it's cooperative multitasking between the goal level and behaviors. It's preemptive multitasking at the instinct level and the 2 levels above it, which is the behavior level and the goal level. So that's basically how Whiskers works. Let me get back. Okay. Get set up here a second. Okay. Gonna share the screen. So I sold about 2,000 of these robots into technical education back in the 90s for about 10 years. So probably I'm estimating between 50 and 100,000 junior high and high school kids went through the Whiskers curriculum over the lifetime of the product, you'll notice that, so this is a 10-day curriculum. So in 10 hours, you know, it's actually probably 45 minutes, not an hour, 45-minute classroom time, and 10 sessions. Kids actually learned how to the art of programming. They knew the basics of programming on this fun little robot who gets upset, gets mad. It doesn't just run programs. He has behaviors. He's happy, he's sad. So I have a little story here. I wrote a story about robotics. So this is how the triune brain maps to our brain. When I created the triune brain, the 3-level architecture, I first created 2 levels, which is just the instincts and the goal level. So the goal level is simply your foreground processing on the computer. The instinct level is operates in the background, and that's in an ISR. So the instincts acquire all the information, reads all the sensors, and updates shared variables. I call them registers. They're typically 8-bit in value, so I call them registers. And each sensor has a group of registers. So let's look at the whisker. So whisker has a flag that says that at some point in time in the past, the whisker has touched something. Okay, so that's a flag. Then it also has a motor override register, which has up to 9 different motor commands. So it could be left wheel forward, left wheel right, you know, with the right wheel, you know, stationary, and same thing on the right wheel. Both wheels forward, both wheels back, pivot left, pivot right. So what you do is you load each instinct with the motion behavior that you want. So on the left whisker, if you're doing collision avoidance, you want to pivot right. On the right whisker, you want to pivot left, for example. He's got 4 optical sensors, 2 looking forward and 2 looking out the sides. Now the optical sensors have more registers. Each optical sensor has the triggered flag, right? It also has, it captures, it first samples the ambient light into, you know, LED off register. And then it samples, this is from an ADC, so it's you know, it's relative to the light. And then it turns the LED on, it samples that, puts it in the second register, which is the eyes on register. And then it's got a third register that the ISR will subtract those 2 values and come up with the delta. So if there's nothing in front of the robot, it's going to be, you know, the delta is going to read from 0 to 4, like just because there's some noise in the system, right? So you need a little bit of hysteresis. So you might say that any value over 10 is actually seeing something. Now, there's another, and then also you have the motor override register. So based on whatever motion you want the motors to go, you load that particular LED with the motion that you want. And whenever the light is above your trigger level register, which is looking at, you know, just the reflected light register, right? Then it's going to do an override for as long as the robot sees something. And as soon as it stops seeing something, the motor override terminates. But as soon as it sees something, it does set the, you know, I've been triggered register. So if you think every single sensor in Whiskers has a flag register that has been triggered, including I monitor the current through the motors. So that means his whole chassis is a sensor of last resort. He may, like when there was a Thinking Forth book down there, and he can't see it because it's too low, but if a wheel hits it, he can sense the increase in current and he can react to that. So his body is a sensor of last resort. Now, so that's the goal level and the instinct level. When I first designed my, I was working on robotic control, I had those two levels. Now the problem was, what happens if you have, if both whiskers are activated? Now they can be activated asynchronously. They don't have to be activated at the same time. But if they're both activated, what I really want to do is I want to back up for a period of time. I want to do a right pivot or a left pivot, and then I want to go forward a foot and then pivot another 90 degrees and terminate the behavior. So when you saw Whiskers playing a song, Blow the Man Down, that was in the goal level. So when you saw him, a behavior activate, I used different sound effects for the delay word. So when I want him to pivot 90 degrees, I make the sound about what it takes for the robot to pivot 90 degrees. And that way you can tell when a behavior fires because he's making a different sound. And when the behavior terminates, then obviously he starts, singing the song Blow the Man Down again. When I added that to it, I created, in nature, it's called the triune brain. I was at I was not trying to emulate the triune brain when I started. I was just solving engineering problems. The goal level and the instinct level, just those two just didn't cut the mustard. I wanted to be able to train the robot like you train a child. If you're in this situation, do this thing. And I want that training to come out when the robot's, has that problem, right? So then I was at a trade show and I was talking to a biologist woman about this, and about the functionality of my three levels. And she goes, "Oh, that's the triune brain." And I said, "Well, what's that?" And that's when I started calling it the triune brain. If you do a web search on it, and there's a Wikipedia on the triune brain. So basically, the cerebral cortex maps to the goal level. The goal level is the foreground task. So in the goal level, you'll be doing things like, using LiDAR to find the door, right? You scan and the LiDAR finds the door. And let's say the door is at 270 degrees compass heading. Then I have a behavior. It's the last behavior in the list, in the chain. The last behavior is stay course, or stay on the compass course. So let's just say the goal level says, "Hey, robot, I want you to go to 270 degrees because that's the door I want to go out of." The compass says, "I'm at 250 degrees." So it will differentially steer the robot so that it's back on course to 270 degrees. And it's the interaction between the three different levels that creates the intelligence. The limbic system is it's like our breathing as part of the limbic system. It's automatic, but you can override it. So the limbic system has things like our feelings and other things. So it maps to that. Oh, the other thing, the way I implemented the behavior level is it's a task list. So basically, we know, every fourth word has a code field address, CFA. So I put the CFA in this task list and it just goes through and it executes it. And what's important about that is I have a word called priority. So if you say one priority add task, a double whisker hit, whatever you called it, it's going to put that behavior right at 1, and it'll push any other behaviors down. So whatever behavior was at 1 is now 2. And so if to control the way the robot reacts, you prioritize the behaviors, because whichever one matches first is going to be executed. A behavior can reload the task list. So let's say you're doing collision avoidance, and it's a fight or flight situation, and now you want the robot to fight. Well, that's the opposite of collision avoidance. You get a double front whisker hit, you want to drive forward, you want to attack. So a behavior can completely reload the task list, add or subtract behaviors, and totally manipulate it. I haven't done a lot of work with that capability, but that's the idea behind it. So goals and learning is your foreground task. Behaviors and tasks is a task list that's being executed about 10 times a second. You don't need to go any much faster than that. Instincts are about a 1 kilohertz rate. So that's how it maps. So and I wanted to try to put most of these sensors and stuff that say a cat would have. So touching, seeing is a 4 independent sensors, feeling is the load or drag on the robot. Hearing, he's got a microphone. One of the behaviors or code that I wrote, the robot would sit there and pivot like 10 degrees at a time. It would measure the amount of sound, and wherever the peak sound, and it would record the compass heading, and whatever the peak sound was, he would take off in that direction. So if you were talking to Whiskers, he could find you, what direction you're at, and take off and go to you. And then speaking, of course, is the speaker, and he plays songs, and he makes a bunch of different sound effects. So here's the different sensors, and basically you just type in sensors, enter, and you get this list on your RS-232 screen. So you do use a terminal window to talk to Whiskers. And so here's the left front sensor, and it's giving you the on and off value, and then the difference is right here. This is the flag register, it's an obstacle, so -1s are trues. But this is what the trigger levels are set at, so it's a differential of 10 between these two values would create a true. So these two values are less, the value is 6, and your trigger level register is 10, so it's not going to trigger. There's some other, some sensors are virtual, like the compass. After I designed Whiskers, the hardware, I realized that a compass is super important to do a navigation. Today we'll use a compass, chip, but back in that day, I didn't have a electronic compass on Whiskers. So I made a virtual compass by virtue of, I basically counted the PWM on time for the left and the PWM on time for the right, subtracted them, and I made an algorithm that basically made a crude compass, and it worked pretty well, actually. So these are flag registers. This is a collision register. If any sensor is triggered, the collision register will have a true in it. So the Whiskers got sends, got lights. Stalls is the motor stall. It's got the battery value. So there was a behavior for a low battery where it would stop and start crying because it wants to be fed. So, the code is like Leo Brody says, make it English. So 20 trigger factors. So that makes it, and this is what the students would do interactively. So you change the trigger factor. When you typed in calibrate, all of the instinct level registers were updated with this value. So if you made it 20, he sees less, he'll see, he won't see as far away, but it'll be very, you know, it won't get false triggering. But at 5 trigger level, Whiskers gets nervous because there's enough fluctuation in the light around where his values are too close together, and it'll actually make him kind of fidgety. So everything kind of maps to being, you know, an animal, you know, sort of thing. Default instincts mean that's basically collision avoidance. So now the kids have Whiskers up on some books, and they got the serial cable, and they're working with the computer terminal program and typing these commands in. I also had a word called remember, and what remember did is it basically stored here into a variable. So the next time it rebooted, all of the words that were created that are in the SRAM, it'll start at the top level word. Forget means you can forget down to a word. Disable and enable is for turning basically the interrupt service routine on and off. Whisker. So I kind of, you know, equated him to a cat. So I put him on books, and this is what the RS-232 window would come up, and it's telling the trigger levels. Okay, everything's in FORTH. If the kids want to program in, the kids are programming in FORTH, by the way. I did not hide that. I don't believe, you know, you always want to build on top of FORTH and let your users, you know, program in FORTH as well. Don't hide FORTH. So here we're gonna learn the movement words. So there's forward, stop, back up, reverse direction. Well, whatever direction the robot's going, it'll reverse the bits, right? So that means if he's going forward, he'll go backwards. If he's doing a left pivot, he'll do a right pivot. If he's doing a left wheel forward, he'll do a left wheel reverse. Number of seconds is just a delaying word. Default instincts, like I said, puts them in the collision avoidance mode. So then they experiment with these words, and they see the behavior of the robot. So here we're chaining words together, right? This is when you program in FORTH, make it English. Try to program in English. It's the best way to do it. So forward 3 seconds stop is actual code. You can teach this to your 8-year-old, right? Forward 3 seconds stop. If your kid knows English, they can program the robot. We have 10 chapters, and every chapter there's an exercise they have to do. So I have them type those out. And so this is a real simple one. So default instincts forward, Whiskers just tries to go forward, right? So disconnect the computer cable, observe, he goes until one of his sensors sees something and he turns away. So we're kind of explaining what's going on in robotics here. So then the second task, how to teach Whiskers new words. So on day 2, they're learning FORTH programming. Look at that. So they're learning that you put in a colon, space, name of your word, all the words he's going to call, and semicolon. Day 2, they're learning FORTH. So, and it's funny, kids, I didn't get, you know, you would think I'd get hundreds of tech support calls. I got like 0. Now I did sell them through 2 major distributors in tech ed. So there's the 3 top distributors are Pittsco, Paxton Patterson, and LabVolt. I sold them to number 2 and 3, Paxton, Patterson, Level, and I did give their internal people training, and they also had a Whiskers there, and I never got tech support calls, which I thought was kind of amazing, actually. So now the words they're going to explore this time, they're going to explore defining new words. They're going to explore periods, seconds, and remember, and a word called whale. So it's a different sound effect. They're going to explore these. Enable and disable basically turns the ISR on and off. So we have them type in words. So type the following. Okay, colon space move forward 10 period stop, and type in words, and look, you see move, right? Move's the top level word. You type in move CR, so they're learning about interactively, working with Forth. And you type in. This time we're going to type in remember, going to reboot the machine, and they're going to see that move is still there. So they're learning that Whiskers can remember the words that they taught them. So now I have them add some more words. One's called noise, 50 to whale. So 50 is kind of the frequency range that the whale command will do, and 2 means it's going to do 2 cycles of it. And so they're testing, they're running these different tests, and they type in remember, and they test each word individually. They type in words, and they see that they've added these words to Whiskers' vocabulary of words. And then they are going to learn about forget. And lo and behold, the words disappear when they type in words. So these kids are learning Forth day 2. Let's see. Okay. So acceleration and deceleration. So I have some words for doing acceleration and deacceleration. One's called ramp up. You get the rate and the speed. Ramp down is just the rate because you're starting at whatever speed you're running at. Forward, back up, stop, left, right. You guys already know what that is. So then they got them on the okay, now they got them on the floor. I had a 20-foot RS-232 cable so that they could do stuff on the floor. Today in modern times, I would make it use the Bluetooth. So I am working on a new board with Brad and Dr. Ting's ESP32 Forth. So been working on it for a while though. Anyway, we'll get that going. So we're going to port this Triune OS to the new board, and then it'll all be open source and open hardware, so you guys can learn from it. So anyway, they put in 0 left speed, 0 right speed, forward 10 feet, and then the robot's not going to move because well, actually, so it's going to stop, but ramp up is going to set it to 100, but forward to 100 ramp up. Now, as far as English goes, I think what I would change this to is we would put in the name. So forward, maybe, let's see, this is the rate. This is the rate that you're going to ramp up. So basically in a do loop, increasing the speed, this is how fast it's going to increase. And then it's going to go to a speed of 100. So I would probably put 2 space rate space 100 speed space ramp up. So ramp up would have to be a little maybe a little smarter, and the rate and speed maybe puts an item on the stack, and then ramp up gets smarter. That way it's more English-like. We want to be English-like. Kids didn't have a problem with this format, but I just think about that. So then they do a series of experiments, and they always have to solve a problem at the end. And guess what they have to do? They have to write forth code. That's how they have to solve every problem in my master curriculum. They have to write their own forth words and test. So here's what they have to do here. Okay, so compass and calibrating pivots and turns. So I told you I built a virtual compass because I did not have a real compass inside. So I basically made it using the on times of the pulse width modulation differential signals, you know, on the left and the right wheel. So you have to basically calibrate the compass, and you put it on the floor, and then you have it pivot 360 degrees, and you adjust the value so it kind of tweaks it so you get 360 degrees. So that's what this is about. Obviously pivots uses the compass. So here we're showing them how to use a shortcut. You know, I'm not a very good typer, so instead of left, I want to type in L. I want to type in right. If I'm doing a quick, quick debugging of my words, I'll make a hotkey in forth, which is just a simple letter, right? Colon space your letter, and then whatever words that is going to call, and then semicolon, and that's how you do hotkeys in forth. And I remember them so that when I turn them off and on again, it'll save in the SRAM. So they go through that. By the way, all of this is Peter's put in a GitHub, which Peter, would you put that in the chat? I uploaded this manual.
No problem.
Yeah, I uploaded the manual, I uploaded this curriculum, and I uploaded the entire source code for the Triune OS. I had uploaded some source code before, and one of the newbies made a comment on the FORTH2020 group that he thought it made it really easy to learn forth by going through, looking at the source code. So yeah, so anyway, you can see that they're getting more and more, learning more and more about forth. They're learning about debugging right now. They're learning new words. Every chapter they're going to learn new words. This is all actual code. Left turn 360 degrees stop, right? That's the way that I chose the words. Is I wanted the words. I showed you the odd-deem voice recognition. My goal long term was to have a voice recognition front end. Back in those days, the only voice recognition board cost like $1,000 and plugged into the back of a PC. So I actually got one of those boards and I hooked it up to the serial, because it had a serial port interface. And I used forth, right? I used forth running on the PC, running the voice recognition engine, and then had a serial line coming to my controller. And this is a big robot. So anyway, that's how I'd make some of my larger robot systems. So now on exercise 4. So the kids, this is their 4th exercise. They're going to go get a Coke. So we got to learn some things about. This is their problem solving exercise. They're going to write get Coke in this. So basically, they're just going to have a robot go out, turn around, and come back to them. So pivots and turns. These are all words that you're going to have to implement on your own robot anyway, and I'm using English. So, maybe you can pattern your words with mine. We can kind of make it a standard. And if you got a better English way of doing it, I'm all ears. So they're going to learn about pivots, which is pivot about the center of the robot. Turn is about turning about one wheel or the other as the pivot point. And so they're going to write just updates a variable in memory, and then turn accesses the variable. So this is a way to help create English-like commands for Forth. Is you can use variables, and you can make like write would be, you know, storing, say, a 1 in the variable, right? So the way I'd code it is I would create a variable called with a small v in the front and turn. So I know that the small v turn variable is associated with this turn, so I don't forget it. I like to keep things simple. So then write is simply a constant that updates the v turn variable, and turn reads the variable and then executes you know, whichever motor command is necessary. So this is a way to allow English parsing, which is I'm a big fan of. You know, computers are so damn fast today. There's no reason why we can't do this kind of stuff. So now they're it's pivoting about, you know, the left wheel. When you say left turn, it'll pivot about that, going that way. You said right turn. Now they're learning about degrees. So right turn 90 degrees stop. You know, that's English, right? Every kid knows that. You know, they'd have to learn C syntax. So, or Fortran or Pascal or anything else. This is the beauty of Forth, you know, right? I really encourage you, when you create words in Forth, think of talking to the robot. It's okay to have a longer word and make, you know, maybe add more variables to your system so that you're making the parsing more English-like. This is the power of Forth, and let's use that power. So let's make our stuff as English as possible. So they're learning about turns and degrees, and then they have to solve a problem. So this time they're gonna write square, right? But they've already learned colon definitions, and so they're gonna write a colon definition to make a square. And here, hint, define 2 words first. One's called leg, so I'm teaching them factoring. Factor your code. So first word is leg, and then turn around, and you know, and then define square using multiple words. In other words, factor your code, don't do it in 1 word. That's lesson number 1 in Forth. So now I have words for doing velocity and speed control and arcs, and so they learn these words. These are the words that they're gonna learn. So let's just say a behavior wants to change the speeds. So I have words for like saving the speeds. So maybe in a behavior that's going to change the speed from the goal level. In the behavior, I'll put save speeds in the very beginning. I'll do whatever I want to do to get out of the situation. And then when I restore speeds, then, you know, it's the same speeds that the goal level was using. So I have a lot of words for save instincts, restore instincts, default instincts. You can create a word for attack instincts. You can change all the instincts. So instead of being a collision avoidance, it's attacking you. And you can make a behavior that, let's say when the robot gets frustrated, it switches over to the attack mode and starts attacking you. This kind of behavior really gets kids interested in programming and robotics. So they're learning about these different techniques in this one. And so now I want them to program a figure 8. You know, that's on exercise 6. So these kids in 6 times 45 minutes are all the way up to like programming figure eights. Sound effects. Whiskers has a lot of sound effects words. We want to make this a fun robot. So whale takes a range. So that's the range of the frequency and the number of times you want to go through the cycle. I have another one called warble. I have one
you just
called
have
laser.
to do a ton of research about turtles now.
What's that?
Do we know which turtle kind?
Which what? I didn't hear that.
Me too.
All right, so there's another one called tones, and then up, down, and I have one called bird call. So what I like to do is when I create a behavior, instead of saying right pivot 90 degrees, I'll put, somebody's got their mic open. We're recording this. So I use these type of words. So if I want to go 90 degrees, I will calculate the parameters to these words. So I get a 90-degree delay. And that way you can tell from the sound which behavior was triggered. It turned out to be very handy. I was just trying to, add a bunch of different sounds that that would be useful for the robot. So there's one called laser. If you type in 100 laser and 500 laser, you get a different laser sound. And so they're experimenting with these words. And then they come down, there's bird call, got a nice little bird in there. And here's an up down sound. I didn't have a great name for that. So create a new word called sound off. They're gonna write some more code. Now